1. Where the solar system really ends. Unexpected boundaries. Where exactly does the solar system end? The answer seems simple, but it isn't. For centuries we thought the edge was at Pluto. Then we discovered the Kuiper belt beyond Neptune. But even that isn't the end. In fact, there are at least 3 different boundaries, depending on what you consider the solar system. And the most distant one is so far away that it defies our understanding of distance. The first boundary is where the planets end. Neptune orbits at about 4.5 billion kilometers from the Sun. It's the last giant planet. Beyond it lies the Kuiper belt, a region filled with icy objects that extends to about 7.5 billion kilometers. Pluto lives there, but that's still not the real edge. The second boundary is much more distant. It's called the heliopause. This is the point where the solar wind, that constant stream of particles the Sun fires in all directions, finally stops. The solar wind travels at absurd speeds, over 1.6 million kilometers per hour, but eventually it encounters resistance. Interstellar space pushes back, and somewhere between 18 and 23 billion kilometers from the Sun, depending on direction, the two meet. There, the solar wind dies. The heliopause marks the limit of the Sun's direct influence. But there is a third boundary, and this one is truly gigantic. It's the Oort cloud, a sphere of trillions of comets that surrounds the entire solar system. It begins where the Kuiper belt ends and extends for almost 2 light-years distance. To put that in perspective, the Sun's light takes only 8 minutes to reach Earth, but it takes more than 2 years to reach the edges of the Oort cloud. That's the true gravitational edge of the solar system. So what's the correct answer? It depends. If you're talking about the Sun's physical influence, solar wind, and magnetic field, then the heliopause is the boundary. Voyager 1 crossed that line in 2012, becoming the first human object to enter interstellar space. But if you're talking about the Sun's gravitational influence, then the Oort cloud is the limit, and no human probe will come anywhere close to it for tens of thousands of years. Here's another surprising fact. The distance to the nearest star, Proxima Centauri, is 4.2 light-years. This means the Oort cloud extends almost halfway to the next star. Our solar system is much larger than it seems. The most distant objects orbiting the Sun exist in near total darkness. The sunlight that reaches them is so weak that the Sun appears as merely a bright star in the sky, not a dominant ball of fire. It takes about 300 years for an object to travel through the Oort cloud and completely escape the Sun's gravitational influence. Even traveling at Voyager 1's speed, the fastest probe ever launched, it would still take 300 years to completely traverse this final region. And something curious happens at the edge. Temperature doesn't drop as expected. Actually, at certain points of the heliopause, temperature spikes to millions of degrees because of the shock between solar wind and interstellar medium. The solar system has no clear line where it ends. It's a series of layers, each defining a different type of boundary. And in the most distant regions of these layers, there are mysteries we're only beginning to understand. Objects that shouldn't be there. Orbits that defy explanation. Some of these objects behave so strangely that astronomers began suspecting something bigger. Several icy worlds in the region beyond Neptune have elongated orbits that all point in the same direction. The chance of this happening naturally is less than 1%. Something massive must be pulling these objects, and that something could be a giant planet we've never seen. 2. There may be a 9th planet. 10 times larger than Earth hidden away. Is there a giant planet hidden in the far reaches of the solar system? Many astronomers believe so. They call it Planet 9. And if it really exists, It's an absolutely massive world, about 5 to 10 times the mass of Earth. But here's the problem. Nobody has ever seen it. No telescope has ever captured its image. So why are scientists so certain it's there? The evidence comes from something strange happening with distant objects in the Kuiper belt. Several of these icy objects, small worlds orbiting beyond Neptune, have extremely unusual orbits. Their orbits are elongated, tilted, and all point in the same general direction. This shouldn't happen by chance. The probability of this occurring naturally is about 0.0007%. Something massive must be pulling these objects gravitationally. In 2016, 2 astronomers from the California Institute of Technology, Mike Brown and Konstantin Batygin, published a study analyzing 6 of these objects. They ran computer simulations trying to explain these strange orbits. The only explanation that worked was the existence of an undiscovered giant planet, a planet that orbits the Sun at an average distance of about 56 billion kilometers. That's 20 times farther than Neptune. Planet 9, if it exists, takes between 10,000 and 20,000 Earth years to complete a single orbit around the Sun. It's so far away that surface temperature would be close to 226 degrees Celsius. And here's the challenge. It's in such a vast region of the sky that finding it is like looking for a needle in a haystack the size of a continent. Telescopes need to scan millions of stars, each one potentially mistaken for the planet. But why have we never seen it before? The reason is simple. It's incredibly dark. The sunlight reaching it is so faint that it reflects almost nothing back. Plus, it moves very slowly across the sky. So slowly that even observing for years, it would be hard to distinguish its movement from background stars. That's why modern telescopes are being used to make repeated scans of the same area of sky, looking for anything that moves. Some scientists have proposed alternative theories. Maybe it's not a planet, but rather a cluster of smaller objects, creating a combined gravitational effect. Or maybe it's a primordial black hole the size of a grapefruit, with the mass of several planets. But these ideas are even more speculative. The Planet 9 hypothesis remains the most accepted explanation. Since 2016, more objects with strange orbits have been discovered. Each new finding strengthens the case for Planet 9. An object called Far, Far Out was found in 2021, orbiting 18 billion kilometers from the Sun. Its orbit also appears to be influenced by something massive. Another object, called 2015 BP519, has an orbit perpendicular to the solar system's plane. This is extremely rare, and again, the best explanation is an undiscovered giant planet. If Planet 9 is confirmed, it would be the greatest astronomical discovery of the century. It would change our understanding of how the solar system formed. It would also raise questions about how many other planets could be hidden in the darkness. But even without visual confirmation, the indirect evidence continues to grow. The Vera C. Rubin Observatory, which began operations in 2025, is scanning the sky with unprecedented power. It can detect objects 100 times fainter than previous telescopes. If Planet 9 exists, this observatory will probably find it in the coming years. And when that happens, we'll have to rewrite the textbooks about the solar system. But while we search for this hypothetical planet, we already know of real objects with orbits so extreme they defy explanation. One of them is so distant that it takes more than 11,000 years to complete a single orbit around the Sun. The 3 Sedna. The most distant object takes 11,000 years to orbit the Sun. Sedna is one of the most mysterious objects in the solar system. Discovered in 2003 by astronomer Mike Brown and his team, it orbits the Sun in such an extreme trajectory that to this day nobody can fully explain how it got there. Its orbital period is approximately 11,400 Earth years. This means that since the last time Sedna was at its closest point to the Sun, human civilization didn't even exist. We were still in the Ice Age, and when Sedna returns to that point thousands of years from now, our current societies will be ancient history. Sedna's orbit is absurdly elongated. At its closest point, called perihelion, it approaches about 11.4 billion kilometers from the Sun. That's already almost 3 times the distance of Neptune, but at its farthest point, aphelion, Sedna stretches to an incredible 140 billion kilometers. To put that in perspective, Pluto orbits at only 5.9 billion kilometers on average. Sedna goes 23 times farther. The strangest thing about Sedna is that it never comes close to any known planet. Its orbit isn't influenced by Neptune, Uranus, or any other mapped object. So how did it get there? How does an object reach such an extreme orbit without interacting with anything? That's the question astronomers have been trying to answer for more than 20 years. One theory suggests Sedna was ejected into its current orbit by a massive planet we don't know about, perhaps Planet 9. The gravity of this hypothetical planet could have pulled Sedna outward, throwing it into its current orbit. Another theory proposes that Sedna was gravitationally captured during a close encounter with another star billions of years ago. The Sun may have passed near another star in the stellar cluster where it was born, and the combined gravity threw Sedna outward. A third, more radical theory suggests that Sedna may have been captured from an entirely different star system. Sedna is about 1,000 kilometers in diameter, roughly 2/3 the size of Pluto. Its surface is reddish, probably covered by a mixture of methane, nitrogen, and water ice. Surface temperature varies between 240 and 12 degrees Celsius, depending on where it is in its orbit. When farthest from the Sun, Sedna experiences cold so extreme that almost all material freezes into solid rock. The sunlight reaching Sedna at its farthest point is 6,000 times weaker than on Earth. The Sun would appear merely as a bright dot in the sky. No larger than Venus appears to us. One day on Sedna lasts about 10 Earth hours. This is based on measurements of how its brightness varies, indicating the object is rotating. But beyond that, we know very little about its composition or surface characteristics. Sedna is not alone. Since its discovery, other objects with similar orbits have been found. One of them, called 2012 VP-113, has a perihelion even farther than Sedna. These objects are called sednoids and form a population that may contain thousands of worlds. All of them share extreme orbits that cannot be easily explained, and all of them point to the possibility of something massive influencing this region. Currently, Sedna is approaching the Sun. It will reach its perihelion around the year 2076. When that happens, it will be at its closest point for the next 11,400 years. After that, it will begin its long journey back into darkness, and it won't return until approximately the year 39,500. The discovery of Sedna was a pivotal moment in astronomy. It proved that there are objects in the solar system that don't follow the rules we knew, and it wasn't the only discovery that changed everything. Another object found years later caused such a big debate that Pluto lost its status as a planet, for Pluto was demoted because of objects at the edge. In 2006, Pluto lost its status as a planet. The decision sparked outrage. People felt attached to the 9th planet they had learned about in school. But the demotion wasn't arbitrary. It happened because astronomers discovered objects at the edge of the solar system that were just as large as Pluto, and in some cases, even larger. The problem started in the 1990s, when astronomers began finding more objects in the Kuiper Belt. At first, these objects were small, But as telescope technology improved, larger ones were discovered. In 2005, an astronomer named Mike Brown found an object that changed everything. It was called Eris, and it was slightly more massive than Pluto. This created a crisis. If Pluto was a planet, then Eris should be one too. And if Eris was a planet, then dozens of other similar objects should also qualify. The International Astronomical Union held a meeting in Prague to settle the issue. They needed a clear definition of what makes a planet. After intense debate, they established 3 criteria. A planet must orbit the Sun. It must be massive enough that its gravity pulls it into a roughly spherical shape. And critically, it must have cleared its orbit of other debris. This third requirement is what disqualified Pluto. Pluto shares its orbital space with thousands of other objects in the Kuiper belt. It hasn't gravitationally dominated its region. Neptune, by contrast, has cleared its orbit. It either absorbed, ejected, or captured everything in its path. Pluto simply isn't massive enough to do this. Its mass is only 0.2% of Earth's mass. It's even smaller than Earth's moon. The decision was controversial. Some scientists argued that the clearing the orbit requirement was too strict. Earth hasn't completely cleared its orbit either. Asteroids still cross Earth's path, but the difference is one of degree. Earth dominates its orbital zone. Pluto does not. The vote passed, and Pluto was reclassified as a dwarf planet. But here's the interesting part. The discovery of Eris and other large Kuiper belt objects didn't just demote Pluto. It revealed an entire population of worlds we didn't know existed. The Kuiper belt contains hundreds of thousands of objects larger than 100 kilometers across. Many of them have moons, some have atmospheres. They're not just rocks. They're geologically interesting worlds. Pluto itself turned out to be far more complex than anyone expected. When NASA's New Horizons spacecraft flew by in 2015, it revealed a world with active geology. Pluto has nitrogen glaciers that flow like ice on Earth. It has a heart-shaped region called Tombor Regio that appears to be resurfaced regularly. It has mountains made of water ice as hard as rock. This isn't a dead world, it's active. The demotion of Pluto also highlights how science evolves. Definitions change as we learn more. In the 1800s, Ceres was considered a planet. Then more asteroids were discovered, and Ceres was reclassified. The same thing happened to Pluto. It's not about disrespecting Pluto. It's about understanding that the solar system is more diverse than we thought. Today, there are 5 officially recognized dwarf planets: Pluto, Eris, Haumea, Makemake, and Ceres. But there are likely hundreds more waiting to be confirmed. Some of them are so far away that we've barely seen them. And the one that caused all this trouble, the one that dethroned Pluto, is a world even more distant and mysterious. 5. Eris. The world that killed Pluto as a planet, Eris, is the most massive dwarf planet in the solar system. It's 27% more massive than Pluto, and it's the reason Pluto lost its planetary status. When it was discovered in 2005, astronomers realized they had a problem. If they kept Pluto as a planet, they'd have to accept Eris too, and possibly dozens more objects like it. Mike Brown, the astronomer who discovered Eris, nicknamed himself the man who killed Pluto. He wasn't trying to be malicious. He was simply following the data. Eris was found using images from the Palomar Observatory in California. It was so far away that it took months to confirm it was real. At first, astronomers thought it might be larger than Pluto in diameter. Later measurements showed it's slightly smaller in size, but more massive because it's denser. Eris orbits at an average distance of 10.1 billion kilometers from the Sun. That's more than twice Pluto's average distance. Its orbit is extremely elongated. At its closest, it comes within 5.7 billion kilometers. At its farthest, it reaches 14.6 billion kilometers. One complete orbit takes 559 Earth years. The last time Eris was at its closest point to the Sun was in 1698. It won't return to that position until the year 2257. The surface of Eris is covered in methane ice. Spectroscopic observations show that it's incredibly reflective. In fact, Eris reflects about 96% of the light that hits it, making it one of the most reflective objects in the solar system. Only freshly fallen snow on Earth comes close to that level of reflectivity. This suggests the surface is relatively young or constantly refreshed. Scientists believe that when Eris is closer to the Sun, some of its methane ice sublimates, creating a temporary thin atmosphere. But when it moves farther away, the atmosphere freezes and falls back to the surface as snow. This process may continuously resurface Eris, keeping it bright and pristine. Eris has one known moon called Dysnomia, discovered in 2005, shortly after Eris itself. Dysnomia is much smaller, with a diameter estimated at 700 kilometers. It orbits Eris every 15.8 days. The existence of Dysnomia was crucial for determining Eris's mass. By observing the moon's orbital period and distance, astronomers could calculate how massive Eris must be to hold Dysnomia in orbit. The name Eris comes from Greek mythology. Eris was the goddess of strife and discord. The name is fitting. Eris caused discord among astronomers by forcing them to redefine what a planet is. Dysnomia, the moon, is named after Eris's daughter in mythology, the spirit of lawlessness. Again, the name is appropriate given the chaos the discovery caused. Despite being more massive than Pluto, Eris is less well known. It hasn't captured the public imagination the same way. There are no missions planned to visit it. At its current distance, it would take a spacecraft more than 24 years to reach it using current technology. And by the time a mission arrived, Eris would have moved to a different part of its orbit. But Eris represents something important. It shows that the outer solar system contains worlds we're only beginning to understand. Objects that challenge our categories and force us to think differently about planetary science. And Eris isn't alone. There are other large dwarf planets sharing that distant, frozen realm. 6. Makemake and Haumea, icy worlds with their own moons beyond Neptune in the frozen reaches of the Kuiper Belt, orbit two more dwarf planets with strange properties. Makemake and Haumea are both large enough to be considered dwarf planets, but they're very different from each other. One is covered in methane ice and resembles Pluto. The other is shaped like a football and spins so fast that a day lasts less than 4 hours. Makemake was discovered in 2005, just days after Eris. It's named after the creation deity of the Rapa Nui people of Easter Island. Makemake orbits the Sun at an average distance of 6.8 billion kilometers, taking 305 Earth years to complete one orbit. Its diameter is approximately 1,330 kilometers, making it slightly smaller than Pluto, but still one of the largest objects in the Kuiper Belt. The surface of Makemake is covered in methane, ethane, and nitrogen ices. Spectroscopic analysis shows it's extremely cold, with temperatures around 243 degrees Celsius. Like Eris, Makemake is highly reflective, with a brightness suggesting a relatively fresh surface. This indicates that some geological or atmospheric process is resurfacing it, though exactly what remains unclear. For years, astronomers thought Makemake had no moons, but in 2016, the Hubble Space Telescope detected a small moon orbiting it. The moon, nicknamed MK2, is only about 160 kilometers in diameter and orbits Makemake every 12 days. The discovery was important because it allowed scientists to calculate Makemake's mass more accurately. The Moon is much darker than Makemake itself, possibly because it's covered in different materials or has been darkened by radiation exposure. Haumea is even stranger. Discovered in 2004, it's shaped like an ellipsoid, roughly twice as long as it is wide. Its dimensions are approximately 2,300 by 700 by 1,000 kilometers. No other large object in the solar system has this shape. The reason is its rotation speed. Haumea spins once every 3.9 hours, making it one of the fastest rotating large objects known. The rapid rotation creates centrifugal force that stretches it into an elongated shape. Haumea has two known moons, Hi'iaka and Namaka, both named after Hawaiian goddesses. Hi'iaka is the larger of the two, with a diameter of about 400 kilometers. Namaka is smaller, around 200 kilometers. Both moons are thought to have formed from material ejected during a massive collision billions of years ago. This same collision may be responsible for Haumea's rapid rotation and unusual shape. There's even more evidence of this ancient impact. Astronomers have identified a family of smaller objects in the Kuiper Belt that share similar orbits and compositions to Haumea. These objects, called the Haumea collisional family, are likely fragments from the same collision that created the moons. This makes Haumea unique among dwarf planets. It's the only one with a confirmed collisional family. In 2017, astronomers made another surprising discovery about Haumea. It has a ring. Observations during a stellar occultation, when Haumea passed in front of a star, revealed a thin ring of material orbiting it. The ring is located about 300 kilometers from Haumea's center and is roughly 70 kilometers wide. This makes Haumea the first dwarf planet known to have a ring system. Both Makemake and Haumea demonstrate the diversity of worlds in the outer solar system. They're not just cold, dead rocks. They have moons, rings, and complex histories. They've experienced collisions, resurfacing, and ongoing geological processes, and they're part of a much larger population of icy worlds that we're only beginning to catalogue. 7. There are thousands of ice worlds we've never seen. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across, but we've only discovered a tiny fraction of them. Most remain invisible, too small and too distant for our telescopes to detect. Yet they're out there, orbiting in the darkness beyond Neptune. Some are as large as moons, others are the size of small planets, and we know almost nothing about them. The problem is distance combined with size. An object that's 500 kilometers in diameter sounds large, but at a distance of 7 billion kilometers, it appears incredibly small. The amount of sunlight it reflects is minuscule. Even the most powerful telescopes struggle to detect such faint objects. And that's just the Kuiper Belt. Beyond it lies the scattered disk, and eventually the Oort cloud, regions even more sparsely populated, but containing trillions of objects. Astronomers estimate there are at least 70,000 Kuiper Belt objects with diameters larger than 100 kilometers. But as of 2025, we've confirmed fewer than 3,000. That means more than 95% remain undiscovered, and those numbers only account for the Kuiper Belt itself. The scattered disk, which extends much farther, likely contains even more objects. These undiscovered worlds vary widely. Some probably resemble Pluto with nitrogen atmospheres and active geology. Others might be more like asteroids, just chunks of ice and rock. Some may have moons. A few might even have rings. But without direct observation, we can only speculate. The Pan-STARRS survey in Hawaii has been instrumental in finding these distant objects. It scans the sky repeatedly, looking for anything that moves against the background stars. When it detects motion, astronomers analyze the object's path to determine its orbit. This method has discovered hundreds of new Kuiper Belt objects since the survey began. But even Pan stars can only see objects down to a certain size limit. The Vera C. Rubin Observatory, which started operations in 2025, is expected to revolutionize this field. Its 8.4-meter mirror and advanced camera can detect objects 100 times fainter than previous surveys. Over the next decade, it's expected to discover tens of thousands of new Kuiper Belt objects. This will give us the first comprehensive census of what's actually out there. Some of these undiscovered worlds may be quite large. There could be objects the size of Pluto, or even larger, that we simply haven't found yet. They might be in parts of their orbits where they're extremely far from the Sun, making them nearly impossible to detect. Or they might have very dark surfaces that don't reflect much light. Either way, they're hiding in plain sight. One fascinating aspect of these objects is their composition. Many are thought to be primordial remnants from the solar system's formation 4.6 billion years ago. Unlike planets, which melted and differentiated, these objects remained frozen. They preserve the original, materials from the solar nebula. Studying them is like studying a time capsule from the birth of the solar system. Some of these objects occasionally get perturbed and fall inward toward the Sun. When they do, they become comets. Every comet we see is a visitor from the outer solar system. Halley's Comet comes from the Kuiper Belt. So do many others. They're samples of those distant worlds delivered to our doorstep. The scattered disk, which lies beyond the Kuiper Belt, is even less explored. Objects there have highly elliptical orbits that take them far from the Sun. These objects were likely ejected by gravitational interactions with Neptune billions of years ago. They're scattered across a vast region of space, making them incredibly difficult to find. And then there's the Oort cloud, which we'll discuss later. It contains trillions of objects, but we've never directly observed a single one. We only know it exists because of the comets that occasionally fall from it. The total mass of all these undiscovered objects is substantial. Some estimates suggest the Kuiper Belt alone contains more mass than the entire asteroid belt between Mars and Jupiter. Recently, astronomers captured the first detailed images of one of these distant worlds, and what they found was completely unexpected. 8 New Horizons photographed a snowman-shaped world. On January 1, 2019, NASA's New Horizons spacecraft flew past the most distant object ever visited by a probe. The object was named Arakoth, a Native American word meaning sky in the Powhatan language. But its appearance surprised everyone. It looked like a snowman. 2 lobes stuck together, one larger than the other, creating a shape unlike anything seen before in the solar system. Arakoth orbits the Sun at a distance of about 6.6 billion kilometers, well within the Kuiper Belt. It's relatively small, only about 36 kilometers long and 20 kilometers wide. But its bizarre shape revealed something important about how planets form. Arakoth isn't the result of a violent collision, it's a contact binary, meaning 2 separate objects gently touched and stuck together billions of years ago. The 2 lobes are remarkably similar in color and composition, suggesting they formed in the same region of the solar nebula. They're both covered in reddish organic compounds called tholins, created when methane and other simple molecules are exposed to radiation. The surface is ancient, covered in craters from billions of years of impacts. But there's no evidence of geological activity. Arakoth is a frozen relic. The gentle merger that created Arakoth tells us something crucial about the early solar system. For decades, scientists debated whether planets formed through violent collisions or gentle accretion. Arakoth provides evidence for the latter. Its two lobes came together at a relative speed of just a few kilometers per hour. That's walking speed. If planet formation involved high-speed impacts, Arakoth would have shattered. Instead, it stuck together. New Horizons captured images showing remarkable detail. The larger lobe is about 21 kilometers across. The smaller lobe is roughly 15 kilometers. The neck, connecting them, is only about 5 kilometers wide. The surface is smooth in some places and heavily cratered in others. Some craters are bright, indicating relatively recent impacts that exposed fresh ice underneath. One of the most interesting features is the lack of a debris field around Arakoth. If its formation involved violent collisions, there should be fragments scattered nearby. But New Horizons detected nothing. This supports the idea that Arakoth formed through a slow, gentle process. Small particles in the solar nebula gradually clumped together, eventually forming larger objects like Arakoth. The mission to Arakoth was a remarkable achievement. When New Horizons launched in 2006, Arakoth hadn't even been discovered yet. It was found in 2014 using the Hubble Space Telescope, specifically to provide a target for New Horizons after its Pluto flyby. The spacecraft had to be redirected slightly to intercept Arakoth, a maneuver that required precise calculations given the vast distances involved. During the flyby, New Horizons passed just 3,500 kilometers from Arakoth's surface, traveling at 51,500 kilometers per hour. It captured hundreds of images and collected data on the object's composition, temperature, and radiation environment. The data transmission took months because of the enormous distance. Signals from New Horizons take more than 6 hours to reach Earth. Arakoth's discovery and study represent a milestone in planetary science. It's the most pristine object ever examined up close. Unlike Pluto, which has been geologically active, Arakoth is unchanged since its formation. It offers a direct window into the conditions of the early solar system, and it proves that even at the edge of the known worlds, there are surprises waiting. But Arakoth is just one object among millions. Beyond the Kuiper Belt lies an even larger reservoir of frozen worlds, a vast cloud that surrounds the entire solar system. 9. There is a cloud with 1 trillion comets. Waiting in the dark, the Oort cloud is the largest structure in the solar system. It's a spherical shell of trillions of icy objects surrounding the Sun, at distances so vast they're almost incomprehensible. The inner edge of the Oort cloud begins at roughly 2,000 times the distance from Earth to the Sun. The outer edge extends to nearly 100,000 times that distance, or about 2 light-years. That's halfway to the nearest star. No one has ever directly observed an object in the Oort cloud. It's too far away. The objects are too small and too dark. But we know it exists because of comets. Long-period comets, those that take more than 200 years to orbit the Sun, originate from the Oort cloud. When something disturbs their orbits, they fall inward toward the Sun, creating the spectacular comets we occasionally see in Earth's sky. The Oort cloud is thought to contain between 1 and 2 trillion objects larger than 1 kilometer across. The total mass is estimated at roughly 5 times the mass of Earth, but that mass is spread across an enormous volume. If you were standing in the Oort cloud, the nearest object would likely be tens of millions of kilometers away. It's incredibly sparse. How did the Oort cloud form? The prevailing theory is that these objects originally formed much closer to the Sun, in the region where the giant planets are now. As Jupiter, Saturn, Uranus, and Neptune grew, their gravity flung countless smaller objects outward. Most were ejected from the solar system entirely, but some were thrown just far enough to remain loosely bound to the Sun's gravity. These became the Oort cloud. The objects in the Oort cloud are pristine relics from the solar system's formation. They're composed primarily of water ice, methane, ethane, carbon monoxide, and hydrogen cyanide. They've never been heated by the Sun. They've experienced no geological activity. They're frozen samples of the original materials from which the planets formed. Occasionally, something disturbs an Oort cloud object. Passing stars, the gravitational tide of the Milky Way galaxy, or giant molecular clouds, can nudge objects inward. When this happens, the object begins a long fall toward the inner solar system. It might take thousands of years to reach the region where the Sun's heat begins to vaporize its ices. That's when it becomes a comet. Some of the most famous comets came from the Oort cloud. Comet Hale-Bopp, which was visible from Earth in 1997, originated there. So did Comet Hyakutake in 1996. These comets have orbital periods measured in thousands or even millions of years. After their brief appearance near the Sun, they return to the darkness for millennia. The Sun's gravity at the Oort cloud is incredibly weak. An object there barely feels the Sun's pull. In fact, the gravity is so weak that passing stars can actually steal objects from the Oort cloud. Every few million years, a star passes close enough to disturb the orbits of outer Oort cloud objects, sometimes pulling them away entirely. One of the strangest aspects of the Oort cloud is how slowly objects move. At its outer edge, objects orbit the Sun at speeds of only about 50 meters per second. That's roughly the speed of a passenger jet. Compare that to Earth, which orbits at 30,000 meters per second. The objects are barely moving at all. The Voyager spacecraft, currently the most distant human-made objects, won't reach the Oort cloud for about 300 years, and it will take another 30,000 years to pass through it completely. Even traveling at 17 kilometers per second, Voyager is barely crawling compared to the scale of the Oort cloud. Despite its vastness, the Oort cloud is gravitationally part of the solar system. The Sun's gravity, though weak, still holds it together. But that gravity reaches even farther than most people realize. 10. The Sun's gravity reaches 100 times farther. Then Pluto gravity is the weakest force in the universe. Compared to electromagnetism or nuclear forces, gravity is practically insignificant. But it's also the longest range force. While the other forces disappear quickly with distance, gravity never disappears completely. The Sun's gravity reaches infinitely far, but its strength decreases with the square of distance. Still, it remains detectable at incredibly vast distances. Pluto orbits the Sun at about 5.9 billion kilometers on average. Its orbit takes 248 Earth years. The Sun's gravitational force at that distance is capable of keeping Pluto in orbit, despite the colossal separation. But here's what's fascinating. The Sun's gravity continues extending far beyond Pluto. It reaches the edges of the Oort cloud at approximately 2 trillion kilometers away. And in some cases, it extends even farther. Astronomers use a concept called the Hill sphere to describe the gravitational reach of a celestial object. The Sun's Hill sphere marks the point where solar gravity can retain objects against the gravitational attraction of other stars. For the Sun, this sphere extends to approximately 100,000 astronomical units away. 1 astronomical unit is Earth's distance from the Sun, about 150 million kilometers. Therefore, the Sun's Hill sphere extends to 15 trillion kilometers. Proxima Centauri, the nearest star, orbits at 4.2 light-years distance. That's approximately 40 trillion kilometers. It seems the Sun's Hill sphere should reach it, but it doesn't quite. Proxima Centauri's gravity also exerts an attraction. In fact, the two stars practically pull on each other gravitationally. The point between them, where the two gravities balance, is closer to the Sun, because the Sun is far more massive. Scientists discovered this by analyzing objects called rogue planets, planets ejected from their native star systems. These objects sometimes capture each other briefly, only to release them again billions of kilometers later. An object's Hill sphere is the zone where it can actually keep another object in orbit. Outside that zone, the gravity of other stars dominates. The Sun's gravity is so weak at these distances that it takes billions of years to exert a significant effect. An object in interstellar space that eventually falls into the Sun's Hill sphere might take 100 million years to spiral noticeably closer. But eventually it will arrive, and when it does, it could become one of the brightest comets ever seen. Curiously, the Sun's gravity doesn't just pull objects inward, it also pushes objects outward. Well, not exactly push, but the combined gravitational effects plus solar wind radiation pressure create a zone where objects can be ejected. Some astronomers believe this is how objects like Planet 9 were thrown so far away. Detecting this distant gravity is usually indirect. Astronomers don't measure gravitational force directly. Instead, they observe how distant objects move. If an object moves in a way that can't be explained by its own inertia alone, then something massive must be pulling it. This was the technique used to confirm that Pluto wasn't the only icy world beyond Neptune. Modern telescopes can detect the movement of extremely distant objects. If an object shifts position in the sky over years, astronomers can calculate its distance and orbit. And if the orbit is strange, say, pointing in a specific direction, astronomers can infer that something else is gravitationally influencing it. The Oort cloud is held together by solar gravity, for now. But in billions of years, the Sun will lose that battle. As the Sun ages and sheds more mass through solar wind, its gravity will weaken. Eventually, objects from the Oort cloud will be captured by other stars or lost into interstellar space. But for now, everything remains under the Sun's dominion. The amount of mass needed to keep these trillions of objects in orbit is surprising. The Sun contains 86% of all the solar system's mass, yet it barely maintains gravitational control over the farthest reaches of its own realm. And here's something even more fascinating. The Sun's gravity reaches so far that objects in interstellar space may be slowly falling toward it, completely unaware they're under its influence. 11. The Sun creates a protective bubble. 18 billion kilometers wide. The Sun doesn't just shine, it also blows. Constantly, billions of charged particles flow outward from the Sun in all directions at a speed of about 1.6 million kilometers per hour. This continuous flow is called the solar wind, and it creates a massive protective bubble around the solar system called the heliosphere. The heliosphere is like an invisible shield. It separates the solar system from hostile interstellar space. Interstellar space is filled with dangerous cosmic rays, high-energy particles traveling at speeds near light speed. These cosmic rays can damage DNA, cause cancer, and create serious problems for any organism exposed to them for long periods. The heliosphere protects us by blocking most of these cosmic rays, reducing exposure inside the solar system by a factor of 1,000 or more. The heliosphere extends far beyond Neptune's orbit. Its inner boundary, called the heliopause, begins somewhere between 18 and 23 billion kilometers from the Sun, depending on direction. Direction matters because the solar system is moving through the galaxy at about 800,000 kilometers per hour. This compresses the heliosphere in front and stretches it behind, like a ship creating a wake in the ocean. In front of the solar system, in the direction of motion, the heliopause is closer. perhaps only 18 billion kilometers away. Behind, the heliopause extends to about 23 billion kilometers or even farther. This creates an asymmetrical shape. It's not a perfect sphere. It's more like a giant comet with a tail. The solar wind isn't uniform. It fluctuates and varies depending on sun activity. During solar maximums, when the sun has more sunspots and greater magnetic activity, the solar wind is stronger. Billions of tons of plasma are ejected in events called coronal mass ejections. During these solar storms, the heliopause can be compressed significantly. Voyager 1 crossed the heliopause in August 2012. It was a historic moment. For the first time in human history, an object made by our species entered interstellar space. Voyager detected clear changes when it crossed. The number of charged particles from solar wind dropped drastically. The number of cosmic rays increased. The magnetic field changed direction. All these indicators confirmed it had crossed the boundary. Voyager 2 crossed the heliopause in November 2018, but at a completely different location. It passed through a region where the heliopause was less dense and effects were less dramatic. This confirmed that the heliopause isn't a sharp line, it's a transition zone, like Earth's thermosphere in the atmosphere. Inside the heliosphere, the solar wind carries the sun's magnetic field. This magnetic field is frozen into the plasma, meaning it moves with the plasma. The magnetic field forms complex structures, including spirals caused by solar rotation. As the plasma flows outward, it carries these magnetic field structures with it. The solar wind isn't constant in speed. There are fast streams, called high-speed streams, that travel up to 800 kilometers per second. And there are slower regions where wind moves at only 300 kilometers per second. These speed differences create complex interactions when fast streams catch up with slow ones. Solar wind temperature is a fascinating mystery. Near the sun's surface, the wind has a temperature of about 1 million degrees Celsius. As it travels outward, we'd expect it to cool. But it doesn't. In fact, in some regions, it gets even hotter. Astronomers still don't completely understand why. Several theories exist, involving heating by Alfvén waves or ionic recombination, but the complete truth is still being investigated. The heliosphere also protects us in a way most people never think about. The solar wind carries space germs with it, bacteria and organic molecules that can travel between stars. Without the heliosphere, Earth would be constantly bombarded with these molecules. Life could have developed completely differently, or perhaps never started at all. So this invisible bubble is fundamental to our existence. 12. Solar wind travels at 1.6 million km/h until it suddenly stops. The solar wind is one of the most constant forces in the universe. It flows continuously from the sun for at least 4.6 billion years. When the sun was born, it began blowing, and it hasn't stopped since. The speed of this wind is extraordinary, approximately 450 kilometers per second, or 1.6 million kilometers per hour. Traveling at that speed, the solar wind would take only 4 days to reach the moon. But then, somewhere between 18 and 23 billion kilometers away, it stops. It simply stops. This seems impossible. How does a stream of particles traveling at 450 kilometers per second suddenly stop? The answer lies in a collision. The solar wind doesn't stop by itself. It collides with the interstellar medium, the extremely rarefied matter filling the space between stars. When the two meet, a dramatic transformation occurs. The interstellar medium is surprisingly dense compared to the pure vacuum we imagine. It consists mainly of neutral hydrogen, helium, and traces of more complex molecules. It also contains cosmic dust, microscopic grains of silicate and carbon. Though extraordinarily rarefied by Earth standards, It's enough to make a difference on cosmic scales. When the fast solar wind encounters the slower interstellar medium, a shock occurs. Astronomers call this the termination shock. It's similar to a supersonic airplane's shock breaking the sound barrier, but on cosmic scale, the shock heats the plasma to millions of degrees. Particles are accelerated, decelerated, and redirected. Voyager 1 passed through the termination shock in December 2004. Its instruments immediately detected the temperature increase and change in particle characteristics. Immediately after, in August 2012, Voyager crossed the heliopause. Therefore, between the termination shock and the heliopause is a region called the outer heliosphere, or Helios Heath, where the decelerated plasma continues its journey. Voyager 2 provided even more interesting data. When it crossed the termination shock in August 2018, it detected different signals than Voyager 1 had found. Temperature was higher, particle density was higher. This suggested the shock isn't uniform. Different regions have different properties. The reason for this variation is that the solar system is moving through the galaxy. As it moves, it encounters different densities of interstellar matter. In some places, it passes through dense molecular clouds. In others, it passes through emptier regions. The termination shock adjusts to local conditions. There's a fascinating concept called bow shock. It's the shock created by the solar system's front as it travels through interstellar space. It's like the shock created by a ship's bow as it cuts through water. Astronomers believe the solar system's bow shock extends to perhaps 230 billion kilometers distance. That would be the real limit of where the solar system ends its influence. Inside the heliosheath, between the termination shock and the heliopause, plasma is turbulent. It's being decelerated, cooled, and redirected. It's acquiring interstellar medium properties while losing solar wind properties. It's a transition zone where physics is complex and still not fully understood. The solar wind is not just particles, it's also energy and magnetic field. All this energy, when dissipated at the termination shock, converts to heat and radiation. That's why temperature rises to millions of degrees. It's an efficient conversion of kinetic to thermal energy. The 450 kilometers per second speed is the average velocity, but there are variations. As mentioned, there are fast streams traveling up to 800 kilometers per second, and during solar storms, even higher speeds are achieved. These variations mean the solar wind isn't a uniform flow. It's more like a turbulent river, with fast currents and slow pools. The fact that solar wind travels so far before stopping is proof of the sun's power. Despite being billions of kilometers away, the sun continues influencing the space around it. Its influence reaches the solar system's farthest edges, and in some cases goes even farther, as we'll see when we explore how the solar system interacts with the galaxy. 13. The boundary moves like a giant breath. The heliopause isn't stationary. It moves, it expands and contracts like a being's chest breathing. And it's not quick breathing. It's breathing measured in years and decades. This movement was detected by Voyager 1 and Voyager 2, confirming that the solar system's edge is dynamic, not static. The main reason for this variation is solar activity. The sun goes through cycles of approximately 11 years. During these cycles, the solar wind changes. During solar maximums, when the sun is at peak activity with many sunspots and frequent solar storms, the solar wind is more vigorous. It pushes farther out. The heliopause expands. As the sun approaches a solar minimum, with fewer sunspots and fewer storms, the solar wind weakens. Less energy flows outward. The heliopause contracts. Objects far away that were in the heliosphere move into the closer outer heliosphere. Voyager 1 detected this contraction. In 2015 and 2016, it recorded changes in plasma characteristics, indicating it was passing through variations in the sheath's thickness. The data suggested the heliopause had moved relative to the spacecraft. The variation was subtle but detectable. There's another factor affecting heliopause position: interstellar medium density. As the solar system moves through the galaxy, it passes through regions of different density. When it passes through a denser cloud, the heliopause is compressed. When it passes through a relative vacuum, the heliopause expands. Voyager 2 provided evidence of interstellar density changes. When it crossed the heliopause, it detected a substantial density change. This confirmed the heliopause isn't just a solar wind boundary. It's also an interface where matter properties change dramatically. Astronomers noticed something curious. The heliopause isn't uniform in distance from the Sun in all directions. As mentioned earlier, it's closer in front, in the direction of solar motion, and farther behind. This asymmetry is similar to how a ship's bow compresses water while the stern creates a wake. There are also variations on timescales of hours to days. The solar wind constantly fluctuates. Sometimes it's stronger, sometimes it's weaker. These fluctuations create waves in the plasma that propagate outward. When they reach the heliopause, they create variations in its extent. Solar storms have particularly dramatic effects. During a large coronal mass ejection, billions of tons of plasma are expelled in short time. This creates a wave in the solar wind that propagates outward at speeds of several thousand kilometers per hour. When this wave reaches the heliopause, it causes significant disturbance. Voyager 1 passed through several solar storms while near the heliopause. It detected effects through changes in magnetic field and particle density. These events demonstrate that the solar system's edge is dynamic and reacts immediately to sun events. There are also long-term fluctuations. Over decades, solar wind density has changed notably. The last 30 years saw about a 4% per decade decrease in solar wind density. Astronomers don't know why. It could be due to long-term solar cycle changes. It could be due to interstellar medium property changes. Or there might be other factors we don't yet understand. A fascinating implication is that the heliopause may be moving farther from the Sun. If solar wind density is truly decreasing, then to maintain pressure balance, the heliopause would have to expand. This would mean the solar system is getting slightly larger. As we advance through the century, this expansion could make Voyager 1 closer to true interstellar space, even though it doesn't move faster. 14. Plasma waves were recorded at the solar system's boundary. The heliopause is not just a pressure boundary. It's a vibrant surface where extraordinary waves form. Astronomers call these Alfvén plasma waves, named after Swedish scientist Hannes Alfvén, who predicted them theoretically. These waves were finally detected directly by Voyager 1's instruments as it approached the heliopause in 2011 and 2012. Alfvén waves are plasma disturbances that propagate along magnetic field lines. Imagine a stretched rope. If you shake one end, the disturbance travels along the rope to the other end. Now imagine the rope is a magnetic field line permeated with charged particles. When you shake the particles, the disturbance travels along the field. That's an Alfvén wave. In solar wind context, these waves are created by variations in plasma velocities and pressures. As solar wind flows out from the Sun, it encounters irregularities. These irregularities generate waves that propagate radially outward and also obliquely. The closer to the heliopause, the more complex these waves become. Voyager 1 recorded regular oscillations in magnetic field magnitude as it approached the heliopause. These oscillations were rhythmic, with periods of days to weeks. The data indicated the presence of structured plasma waves. But here's what's fascinating. In the region just before the heliopause, waves became much more chaotic and violent. This suggested the heliopause is a turbulence region where alpha waves collide, reflect, and create secondary waves. It's like a body of water with two opposing currents colliding, creating chaotic wave patterns. In the zone of about 10 billion kilometers around the heliopause, plasma is in turmoil. Voyager 2 provided more information. When it crossed the heliopause, it also detected plasma variable oscillations, but the pattern was slightly different from when Voyager 1 crossed. This suggested turbulence isn't symmetric. Different heliopause regions have different wave properties. Astronomers use these wave properties to infer heliopause plasma nature. Wave frequency, amplitude, and propagation tell them about plasma temperature, density, and composition. Through this analysis, they discovered the heliopause is a mixture of decelerating solar plasma and accelerating interstellar plasma. A particularly interesting aspect is that waves carry energy. As they propagate, they transfer energy from one place to another. At the heliopause, this energy transfer is crucial. It helps thermalize the plasma, converting ordered motion into random motion, heat. That's why temperature rises to millions of degrees. Waves also confine charged particles. The oscillating magnetic field from waves acts as a magnetic trap, keeping particles in spiral trajectories around field lines. This affects how particles move and how they combine. There's a special wave type called a shock wave. When solar wind hits the termination shock, it creates an abrupt discontinuity. Across this discontinuity, plasma properties change drastically. Voyager detected clear signals of this discontinuity. Crossing it was like crossing a wall. Analyzing plasma waves also revealed instabilities, regions where conditions are so unfavorable that small perturbations amplify rapidly. These instabilities create complex plasma structures, including filaments, vortices, and current sheets. These discoveries have implications beyond the solar system. The same Olfven waves occur around other stars. Studying them here, where we have instruments in place, helps us understand phenomena in exoplanetary systems. The same waves may be creating structures and mediating processes in gas clouds around other stars. Plasma wave detection also confirmed theoretical predictions of how plasma behaves in magnetic fields. It confirmed that magnetohydrodynamics, the discipline describing charged fluid behavior in magnetic fields, was correct in its fundamental calculations. 15. Voyager 1 left the solar system and still works after 48 years. When Voyager 1 launched on September 5, 1977, no one could have predicted it would still be functioning nearly 5 decades later. The spacecraft was designed for a 5-year mission to Jupiter and Saturn. Engineers expected it would be dead long before reaching the edge of the solar system. Yet here it is, in 2025, still transmitting data from the interstellar medium 24 billion kilometers away. The fact that Voyager 1 works at all is extraordinary. Space is hostile. Radiation constantly bombards spacecraft, degrading electronics. Solar panels become less efficient as they're covered with dust. Mechanisms seize up from the cold, but Voyager 1 was built to last. Its designers used redundancy. They included backup systems for nearly every critical component, and they built it before computer chips became the dominant technology. Much of Voyager 1 relies on older, simpler electronics that are more resistant to radiation damage. In 2012, Voyager 1 crossed the heliopause and entered interstellar space. It was the first human-made object to do so. The data it sent back confirmed predictions about what would happen at the solar system's boundary. The density of particles changed. The direction of the magnetic field flipped. The cosmic ray counts increased. Everything matched what scientists expected, yet seeing the actual data was profoundly moving. The spacecraft carries a golden record, a phonograph record containing sounds and images from Earth. It includes music, scientific data, and greetings in 55 languages. If aliens ever find Voyager 1, they'll find a message from humanity. The record was included by Carl Sagan and other scientists who believed in the possibility of contact. Whether anyone will ever find it is unknowable, but it represents humanity's hope of reaching beyond our world. Power is perhaps Voyager 1's greatest challenge. The spacecraft is powered by 3 radioisotope thermoelectric generators, or RTGs. These devices convert the heat from decaying plutonium-238 into electricity. When Voyager launched, the RTGs produced about 470 watts. By 2025, they produce only about 60 watts. That's a decline of nearly 87% over 48 years. Yet somehow, the spacecraft still functions. To keep operating on such limited power, engineers have had to be creative. They've systematically shut down non-essential instruments. The cameras were turned off decades ago. Most scientific instruments have been powered down. Only the essential sensors remain active: the plasma wave detector, the magnetometer, and a few others. Even with these limitations, collecting data is challenging. The spacecraft must carefully ration its remaining power. Communication is another challenge. Voyager 1 sends data at a rate of 160 bits per second. That's slower than a 1970s modem. The signal takes over 22 hours to reach Earth from Voyager 1, and the receiver dishes on Earth must be precisely aligned to catch such a faint signal. Despite this, NASA's Deep Space Network successfully receives data from Voyager 1 regularly. The signals from Voyager 1 are some of the most distant communications ever received. They come from so far away that the light travel time is measured in hours, not seconds. When mission controllers send a command to Voyager 1, it takes over 22 hours to arrive. If there's an emergency, Voyager 1 can't be saved in real time. Everything must be planned in advance. The spacecraft continues to make discoveries. In 2013, it detected a sudden increase in cosmic rays, confirming it had crossed into the interstellar medium. In 2019, it detected the presence of a hydrogen wall, a region where hydrogen gas from the interstellar medium creates a barrier against the solar wind. These discoveries continue to reveal how our solar system interacts with the galaxy. Voyager 1's trajectory will take it toward the star Gliese 445 in approximately 40,000 years. At that point, it will pass within 1.6 light-years of the star, but long before then, its power will fail completely. Current predictions suggest Voyager 1 will cease operations around 2025 to 2026. It will become silent. The signals will stop. An era of exploration that began in 1977 will end. But the spacecraft itself will continue. Even without power, even without the ability to transmit, Voyager 1 will continue its journey. It will drift through space, carrying humanity's message, perhaps for billions of years. It may be found by a future civilization, or it may simply float in silence forever. Either way, it represents one of humanity's greatest achievements, the first object we sent beyond the solar system that still works. 16. Voyager 2. Crossed the boundary in a completely different place. Voyager 2 launched on August 20th, 1977, just 16 days before Voyager 1. Yet despite following a similar trajectory, it took a completely different path through the solar system. It visited Jupiter, Saturn, Uranus, and Neptune, the only spacecraft ever to visit the ice giants. And when it finally reached the heliopause in November 2018, it encountered conditions remarkably different from what Voyager 1 experienced. The difference was profound. Voyager 1 detected a dramatic, sudden change when it crossed the heliopause. Magnetic fields flipped, particle densities plummeted. The transition was stark. But Voyager 2 encountered something different, a more gradual transition. The changes happened over weeks and months rather than days. It was as if Voyager 2 crossed through a more diffuse boundary. This difference tells us something crucial about the heliopause. It's not uniformly structured. Different regions have different properties. Voyager 1 may have crossed through a region of compressed boundary. Voyager 2 may have crossed through a region that was more expanded or had different pressure conditions. The magnetic field changes were particularly interesting. When Voyager 1 crossed the heliopause, the magnetic field direction reversed sharply. But Voyager 2 detected a more complex pattern. The field rotated gradually rather than flipping abruptly. This suggests that the magnetic field structure varies depending on location along the heliopause. Temperature readings also differed. Voyager 1 detected temperatures of several million degrees in the Helios health. Voyager 2 detected temperatures closer to 1 to 2 million degrees. This variation indicates that different regions of the heliopause have different thermal properties. Some regions are hotter than others. The cosmic ray data was particularly revealing. Both spacecraft detected an increase in cosmic rays after crossing the heliopause, as expected. But the rate of increase differed. Voyager 2 showed a more gradual increase, while Voyager 1 showed a sharper spike. This suggests that the cosmic ray environment in the interstellar medium varies geographically. One of the most surprising findings was that Voyager 2's plasma data indicated the presence of magnetic field reversals. Small-scale fluctuations in the field occurred frequently, suggesting turbulence on smaller scales than Voyager 1 detected. This may have been due to Voyager 2 crossing through a more turbulent region of the heliopause. The difference between the two Voyagers' experiences raises an important question. Which one represents the typical solar system boundary? The answer is probably neither. The heliopause is likely highly variable, with some regions resembling Voyager 1's experience and others resembling Voyager 2's. Different parts of the boundary have different conditions. This has implications for understanding other star systems. Around other stars, the edge of stellar wind likely creates similar structures, but how those structures vary would depend on the specific conditions of each system. By studying the heliopause around our Sun, we gain insight into how stellar winds interact with interstellar media everywhere. Voyager 2 also carries a golden record, identical to Voyager 1's. It carries the same messages, the same music, the same hopes for contact. If one is found by an alien civilization, it will carry the same information. If both are found, they'll corroborate the message, a backup of humanity's message sent into the cosmos. Like Voyager 1, Voyager 2 is powered by RTGs that are declining over time. However, Voyager 2 was on a more ambitious trajectory, visiting 4 planets instead of 2. This meant higher velocity requirements and more demanding missions. The spacecraft experienced more stress. By 2025, Voyager 2's power output is similar to Voyager 1's, severely degraded but still functional. Voyager 2 is also following a different trajectory through space. It's heading toward the star Ross 248, which it will approach in approximately 40,000 years. Unlike Voyager 1's eventual encounter with Gliese 445, Voyager 2's approach to Ross 248 will be much closer, only about 3.2 light-years. Whether that makes it more likely to be discovered someday is unknowable. The comparison between Voyager 1 and Voyager 2 reveals something profound. The solar system's boundary is complex and varied. It's not a simple line. It's a region of transitions, turbulence, and variability. Understanding these variations requires multiple data points from different locations. The two Voyagers, launched 16 days apart, have provided that crucial data. 17. NASA can still talk to Voyager. 24 billion kilometers away, the Deep Space Network is one of humanity's greatest engineering achievements. It consists of 3 antenna complexes spaced evenly around Earth, one near Madrid, one near Canberra, Australia, and one near Goldstone, California. These massive dishes, some 70 meters in diameter, are pointed at the sky 24 hours a day. They listen for signals from spacecraft billions of kilometers away. Communicating with Voyager 1 is extraordinarily challenging. The signal arrives at Earth with a power of about 10 watts per square meter per hertz. That's extraordinarily faint. For comparison, the signal from a cell phone at the edge of coverage is millions of times stronger. The Deep Space Network must use the largest antennas available and the most sensitive receivers to detect Voyager's transmissions. The signal takes 22 hours to reach Earth from Voyager 1. This creates a fundamental challenge. Real-time control is impossible. Engineers send commands knowing they won't arrive for a day. If something goes wrong, they can't immediately respond. Everything must be planned in advance. Software updates, course corrections, and recalibrations must all be programmed months or years ahead of time. Yet the system works remarkably well. Engineers at NASA's Jet Propulsion Laboratory can communicate with Voyager 1 regularly. They receive data about the spacecraft's status, its trajectory, and what its instruments are measuring. This data informs us about the interstellar environment surrounding the spacecraft. The antennas themselves are marvels of engineering. The 70-meter dishes at each complex weigh over 2,000 metric tons. They must be precisely positioned to track distant spacecraft. They're cooled to near absolute zero to reduce electronic noise. They're constantly maintained and upgraded with new technology to maximize their sensitivity. The receivers are equally sophisticated. They use quantum-limited amplifiers, devices that can detect individual photons. They use sophisticated signal processing algorithms that distinguish Voyager's signal from the noise. Despite all this, the signal is still so faint that detecting it requires both science and luck. But here's what's truly remarkable. After 48 years, after traveling 24 billion kilometers, after all the radiation and cold and isolation, Voyager 1 still wants to communicate. Its transmitter still functions. Its systems still operate. The engineers still maintain the code that runs the spacecraft. The infrastructure still exists to receive and decode its signals. The data Voyager transmits is invaluable. It's information about the interstellar environment that we can get no other way. It's measurements of cosmic rays, magnetic fields and particles that exist in the vast emptiness between stars. No ground-based observatory can measure these things. No other spacecraft has gone far enough to collect such data. Maintaining the Deep Space Network is expensive and demanding. It requires constant upgrades and maintenance. The antennas are among the largest structures on Earth. They consume enormous amounts of power. They require teams of skilled engineers and scientists. Yet NASA has committed to keeping them operational, in part because of the Voyagers. The moment when Voyager 1's transmitter finally goes silent will be bittersweet. The mission will have lasted longer than nearly anyone predicted. The spacecraft will have given humanity insights into the structure of the solar system and the nature of interstellar space. But the silence will be profound. One of humanity's greatest achievements will stop communicating. Currently, both Voyagers are still transmitting, though their power continues to decline. Engineers estimate that Voyager 1 will likely go silent sometime in 2025 or 2026. Voyager 2 might last a bit longer, perhaps into 2026 or 2027, but both eventually will go dark. and the era of the Voyagers will end. Yet even in silence, they'll continue their journey. They'll drift through space for billions of years. They'll carry humanity's message into the future, perhaps to be found by a civilization not yet born. They'll represent an era when humanity reached beyond its world and successfully sent emissaries to the stars. Few achievements can claim greater significance. 18. Voyager detected a tsunami of plasma in interstellar space. In September 2022, astronomers detected something extraordinary. All 4 spacecraft that had reached interstellar space or near it, Voyager 1, Voyager 2, New Horizons, and Pioneer 10, detected a sudden, coordinated change in the plasma environment. It was as if a wave had passed through interstellar space, simultaneously affecting all 4 distant observers. The wave was triggered by a massive solar eruption. In September 2022, the Sun experienced a series of powerful coronal mass ejections. These are events where billions of tons of plasma are flung outward from the Sun's corona. The material travels through the solar system at speeds of several million kilometers per hour. Eventually, it reaches the heliopause and beyond. What's remarkable is that the wave reached all 4 distant spacecraft, roughly simultaneously. Well, not exactly simultaneously. The timing varied based on each spacecraft's location and the wave's trajectory, but the coordination was clear. Scientists watching the data from multiple observatories recognized that they were all seeing the same phenomenon. The wave was visible as a sudden increase in plasma density and a change in the magnetic field orientation. The plasma wave detectors aboard the Voyagers recorded oscillations in the electromagnetic field. The intensity increased dramatically. It was as if the spacecraft had been struck by an invisible shock wave traveling through space. The phenomenon is called a tsunami informally by scientists, though technically it's an interplanetary shock wave. It occurs when the fast material from a coronal mass ejection catches up to slower material that was ejected previously. The compression creates a shock front that travels outward at speeds of 1,000 to 2,000 kilometers per second. The beauty of having 4 distant observers is that scientists could triangulate the wave's position and velocity. By analyzing the arrival times at each spacecraft, they could determine exactly where the wave was and how fast it was traveling. This kind of multipoint observation is rare in interstellar science. Usually, data comes from a single location. The wave provided an unexpected opportunity to test theories about how plasma waves propagate through space. Scientists could compare the observations with predictions from magnetohydrodynamic simulations. The results were mixed. The predictions got some things right, but not everything. This means there's still much to learn about how plasma waves behave at large scales. The event also demonstrated how interconnected the solar system is. A disturbance at the Sun creates measurable effects billions of kilometers away. Information about that disturbance propagates outward at the speed dictated by physics. The fact that Voyager detected this wave means it can serve as an early warning system for solar activity, in a sense. Scientists used the wave to estimate properties of the interstellar medium. The wave's speed and amplitude told them about the density and temperature of the plasma surrounding the solar system. By analyzing how the wave propagated, they could infer the magnetic field strength in the region. The event also revealed something about the structure of interstellar space. It's not uniform. The wave's properties changed as it propagated. In some regions it moved faster, in others, slower. This suggests there are variations in the properties of the interstellar medium on scales of billions of kilometers. Detecting this tsunami demonstrated the value of having long-lived missions. If the Voyagers had failed even a few years earlier, this data would be lost. The information would exist nowhere else. By maintaining these spacecraft despite their age and declining power, scientists were able to capture unique observations. The event also captured public imagination. News of the wave spread across media outlets. People were fascinated by the idea of a visible phenomenon reaching multiple spacecraft simultaneously. It made the abstract concept of the interstellar medium feel more real, more immediate. More tsunamis will likely occur. The sun remains active. More coronal mass ejections will happen. Each one will send a wave outward through the solar system and beyond. Future observations of these waves will continue to teach us about the nature of interstellar space. And the Voyagers, for as long as they function, will continue to document these phenomena. 19. There is a hydrogen wall, blocking the way out. The interstellar medium is not empty. It's filled with hydrogen, the most abundant element in the universe. Most of it is neutral, meaning it's not ionized. This neutral hydrogen creates a structure at the edge of the solar system called the hydrogen wall, or hydrogen barrier. It's a genuine physical obstacle that the solar system encounters as it travels through the galaxy. The hydrogen wall forms because of the interaction between the solar wind and the interstellar medium. The solar wind is hot, ionized plasma flowing outward from the sun. Neutral hydrogen from the interstellar medium flows inward with the solar system's motion through the galaxy. When the two meet, a charge exchange reaction occurs. Neutral hydrogen captures electrons from the solar wind plasma, becoming ionized. This process creates a structure. On the side of the solar system facing the direction of motion, the solar wind compresses neutral hydrogen into a denser region. The pressure of the solar wind holds back the neutral hydrogen, creating a wall-like boundary. On the other side, the neutral hydrogen flows more freely. Voyager 1 detected the hydrogen wall in 2019, several years after crossing the heliopause. The spacecraft's particle detectors registered a sudden increase in neutral hydrogen density. This was surprising because after crossing the heliopause, scientists expected the plasma environment to be relatively uniform. But it wasn't. There was structure. The hydrogen wall appears to be a few billion kilometers thick, a significant feature on the scale of the solar system. Voyager 1's data suggested it's located at roughly 200 astronomical units from the Sun, or about 30 billion kilometers. That's well beyond the heliopause. The temperature in the hydrogen wall is cold, around 6,000 to 8,000 Kelvin, much colder than the solar wind, but hotter than deep interstellar space. The density is about 0.1 particles per cubic centimeter, which seems vanishingly low, but is actually dense by interstellar standards. The hydrogen wall is significant for several reasons. First, it represents another boundary within the interstellar medium. Just as the heliopause marks the limit of the solar wind, the hydrogen wall marks the limit of the solar wind's influence on neutral hydrogen. Beyond it, neutral hydrogen behaves differently. Second, the hydrogen wall affects cosmic rays. Some cosmic rays can be deflected by the hydrogen wall's density variations and weak magnetic fields. This means different cosmic ray energies might penetrate at different rates. The hydrogen wall acts as a partial filter, affecting what reaches the inner solar system. Third, the hydrogen wall is dynamic. As the solar system moves through the galaxy, it encounters different densities and configurations of interstellar hydrogen. The wall's thickness and position likely change over time. Billions of years ago, the solar system may have encountered a different hydrogen environment. The hydrogen wall is not unique to our solar system. Every star likely has one. As each star moves through the galaxy, its stellar wind creates a similar structure where it meets the interstellar medium. Studying our hydrogen wall teaches us about the general phenomenon. Scientists are still working to understand the hydrogen wall completely. Detailed models of the interaction between solar wind and neutral hydrogen are being developed. These models will help predict what we'll find as we move farther into interstellar space. For now, the hydrogen wall represents another step in the solar system's transition from familiar space to the unknown. It's a marker, a sign that we're leaving home. Beyond it, the interstellar medium dominates. The sun's influence diminishes further. We enter a realm where other forces and other structures take over. And somewhere beyond, even that lies the next star. 20. The pressure of interstellar space compresses the solar system. The solar system is not isolated. It sits within the galaxy, embedded in the interstellar medium, and that medium exerts pressure. The pressure comes from multiple sources: the density of neutral hydrogen and helium, the pressure of the interstellar magnetic field, and the bombardment of cosmic rays. Together, they exert a force on the heliopause that compresses it, preventing it from expanding indefinitely. Imagine a soap bubble. The pressure inside pushes outward. The air outside pushes inward. The bubble's size is determined by the balance between these pressures. The heliopause works similarly. The solar wind pressure pushes outward. The interstellar medium pressure pushes inward. The heliopause is where these pressures balance. The interstellar medium is not very dense. Most of it is extremely thin, with only a few particles per cubic centimeter. By Earth standards, this is an excellent vacuum. But when spread across billions of cubic kilometers and exerting constant pressure, it adds up. The magnetic pressure is significant. The interstellar magnetic field is weak, only about 5 to 10 microgauss in strength. But magnetic energy scales with the square of the field strength. Over enormous volumes, even weak magnetic fields contain substantial energy. This energy exerts pressure on the heliopause. Cosmic ray pressure is less well understood, but significant. Cosmic rays are relativistic particles traveling at nearly the speed of light. They hit the heliopause and transfer momentum. While individual impacts are negligible, the cumulative effect of trillions of cosmic rays is substantial. Some estimates suggest cosmic ray pressure contributes between 10% and 50% of the total inward pressure on the heliopause. The total inward pressure is balanced by the ram pressure of the solar wind. The solar wind particles, streaming outward at 450 kilometers per second, strike the heliopause and transfer momentum. The density of the solar wind is extremely low, but its velocity is very high. The momentum transfer is significant. As the solar system moves through the galaxy, it encounters regions of different interstellar density. When it passes through a dense molecular cloud, the external pressure increases dramatically. The heliopause compresses. When it passes through a region of lower density, the external pressure drops. The heliopause expands. We're currently passing through a region called the local interstellar cloud, a relatively thin region of interstellar material. But we're about to enter a denser region called the G cloud, or Gould's belt extension. When the solar system enters this region, the external pressure will increase noticeably. The heliopause will compress. This compression has consequences. A compressed heliopause is less effective at protecting the inner solar system from cosmic rays. More cosmic rays will penetrate. The solar wind will be compressed into a smaller volume, reaching higher densities. The magnetosphere of each planet will be squeezed, reducing its protection against solar wind particles. The compression also affects comets in the Oort cloud. The pressure changes alter the gravitational stability of outer Oort cloud objects. Objects that were stable might become unstable. Some might fall inward toward the sun, becoming long-period comets. Others might escape into interstellar space. Scientists estimate that when the solar system enters the G cloud in roughly 50,000 years, the heliopause will compress to perhaps half its current size. The cosmic ray flux at Earth could increase. The solar wind environment could change substantially. Life on Earth would not be directly affected due to our magnetosphere's protection, but the environment at the top of the atmosphere could change. Understanding this compression is important for understanding our place in the galaxy. We're not in a permanent, unchanging environment. Our position in the galaxy is dynamic. The conditions around us change on timescales of thousands or millions of years. The solar system is like a ship traveling through an ocean with varying currents and pressures. The compression also has implications for other planetary systems. Every star experiences similar compression as it moves through the galaxy. Some stars likely pass through dense regions frequently. Others rarely encounter dense material. This variation affects the habitability of planets around other stars. For Earth specifically, the upcoming encounter with the G cloud is something to think about, not with alarm, but with curiosity. It's a natural phenomenon that will reshape the environment around our planet. It will test the resilience of Earth's magnetosphere. It will be a significant event in the planet's history. 21. The solar system has a tail. Like a comet, comets have tails. Everyone knows this. As a comet approaches the sun, solar radiation vaporizes its ices, and the solar wind blows the material into a long tail that always points away from the sun. The tail can stretch for millions of kilometers. But here's something surprising. The solar system itself has a tail. It's called the heliotail, and it extends for billions of kilometers behind us as we move through the galaxy. The heliotail forms because the solar system is moving through the interstellar medium at approximately 25 kilometers per second relative to the local stars. This creates a bow wave in front of us, compressing the interstellar material. Behind us, the interstellar material flows around the heliopause and creates a wake, similar to how water flows around a moving ship, creating a wake behind it. The heliotail is asymmetrical. The bow shock forms in front, where the solar system crashes into the interstellar medium head-on. The tail extends backward, where the interstellar material closes back in after being disturbed by the solar system's passage. The tail is probably hundreds of billions of kilometers long, stretching far beyond the reach of the Voyagers to observe. Scientists have never directly observed the heliotail because it's behind us. The Voyagers are currently ahead of the solar system in its direction of motion, so they're approaching the bow shock. By the time either Voyager might pass through the heliotail region, if ever, humanity will be long gone, and the spacecraft will be even more degraded or non-functional. However, we can infer the heliotail's existence through theory and indirect observation. Models of the interaction between stellar winds and the interstellar medium consistently predict a tail structure. The shape and size depend on factors like the stellar wind strength, the interstellar density, and the magnetic field. For our solar system, the models suggest a tail that's surprisingly complex. The heliotail is not empty. It contains plasma that has been swept up and disturbed by the solar system's passage. It contains particles from both the solar wind and the interstellar medium, mixing in a complex dance. The magnetic field in the tail is tangled and knotted, different from both the solar system's ordered field and the interstellar medium's uniform field. Importantly, the heliotail is not permanent. As the solar system moves through different regions of the galaxy, the tail changes. When the solar system passes through a dense molecular cloud, the pressure increases and the tail becomes compressed and more pronounced. When it passes through a low-density region, the tail becomes diffuse and less defined. The heliotail also has implications for comets. Objects in the outer Oort cloud that are loosely bound to the solar system might be stripped away by the drag of the interstellar medium flowing through the tail. Over billions of years, this gradual removal might explain why the Oort cloud might be smaller than theoretical models predict. Other stars have heliocultural too. Every star moving through the galaxy creates a similar structure. Some stars move faster through the interstellar medium, creating more pronounced tails. Some move slower, creating fainter wakes. The structure depends on the star's properties and the local interstellar environment. Interestingly, some stars in our neighborhood have particularly pronounced heliotails because they're moving faster than average. Some are moving at speeds up to 100 kilometers per second relative to the local frame. Their heliotails would be much more pronounced than ours. Observing these structures around other stars helps scientists understand the general phenomenon. The heliotail is also important for understanding the structure of the local bubble, a region of low-density interstellar material where the Sun currently resides. The local bubble is thought to be the remains of a supernova explosion that occurred millions of years ago. The structure of the bubble, including where different stars sit within it, is influenced by the motion of the stars and the heliotails they create. One fascinating aspect is that the heliotail might contain material ejected from the solar system billions of years ago. Ancient solar wind that was swept backward might still be in the tail, mixed with interstellar material. In some sense, the tail is a historical record of the solar system's passage through the galaxy. The heliotail also affects how distant observers would see our solar system. If an alien civilization were far behind us, looking at our solar system from within the heliotail, they would see a very different picture than if they were directly ahead. The tail would distort and obscure the view. It would make detecting Earth from that direction much more difficult. As we continue moving through the galaxy, the heliotail extends further. In billions of years, if someone were to follow our path, they'd see the heliotail as a trail in space, marking where we passed. It's a mark of our journey through the cosmos, and eventually it will dissipate as the interstellar medium restabilizes after our passage. But for a time, we leave an impression in the galaxy. 22. The solar system creates a shock wave in interstellar space. The solar system moves through space at 25 kilometers per second relative to the local interstellar medium. That's not incredibly fast by cosmic standards. Galaxies move at millions of kilometers per second. But it's fast enough to create a shock wave. This shock is called the bow shock or the termination shock. It's created where the solar system's motion compresses the interstellar material. The bow shock is thought to exist at a distance of roughly 230 billion kilometers from the Sun, perhaps even farther. It's well beyond anything we've directly observed, but theoretical models predict its existence based on fluid dynamics principles. When an object moves through a fluid faster than the speed of sound in that fluid, it creates a shock wave in front. For the solar system, the relevant sound speed is not the speed of sound in air. It's the speed of sound in ionized plasma, called the sonic speed or the magnetosonic speed. This depends on the plasma's temperature and density. In the interstellar medium, the sonic speed is only a few tens of kilometers per second. Since the solar system moves at 25 kilometers per second, it's moving slower than the sonic speed. So technically, the solar system doesn't create a true shock. Instead, it creates a bow wave. The material is compressed ahead of the solar system's motion, but the compression is not as violent as a true shock. It's more like a wave that forms ahead of a slow-moving ship in calm water. The water compresses and rises, but it's not explosive. It's a smooth transition. The bow wave compresses the interstellar material into a relatively narrow layer. The density in this layer might be 10 to 100 times higher than the background interstellar medium. The temperature rises due to the compression. The magnetic field is amplified. It's a genuine barrier between the solar system and the interstellar medium beyond. The structure of the bow wave is complex. It's not uniform. Different directions have different compressions depending on the local interstellar conditions. It's probably wrinkled and turbulent, with structures at multiple scales. Detailed models suggest that the bow wave might contain multiple substructures, layers within layers. Inside the bow wave, between it and the heliopause, is a region called the heliosheath. This is where the solar wind has already been decelerated by the interstellar pressure. The plasma here is transitional, neither purely solar wind nor purely interstellar medium. It's a mixing zone. The bow wave is important for understanding how the solar system interacts with the galaxy. It's the first interface between our system and the rest of the universe. Everything else in the solar system exists inside this structure. It's our outer boundary, though we can't see it. The bow wave also protects us. By compressing the interstellar material, it creates a barrier that cosmic rays must pass through. The compression amplifies the magnetic field, which can deflect some cosmic rays. The bow wave thus contributes to the protection offered by the heliopause and the solar system's magnetic field. As the solar system moves through different regions of the galaxy, the bow wave changes. When moving through denser material, the bow wave is closer to the Sun, more compressed. When moving through less dense material, the bow wave is farther out. This variation affects the overall structure and protective capability of the entire heliospheric system. Other stars have bow waves too. Some stars are moving very fast through the interstellar medium, creating pronounced bow waves. These are visible as arc-like structures in infrared observations, where the compression heats the dust and creates visible features. By studying these structures around other stars, scientists understand the general phenomenon better. One of the most famous examples is the star Zeta Ophiuchi, which is moving at about 30 kilometers per second through a region of relatively high interstellar density. The bow wave around Zeta Ophiuchi is visible in infrared images as a beautiful arc shape. It demonstrates clearly what our solar system's bow wave probably looks like, though our own is harder to image because we're inside it. The bow wave will change in the future. When the solar system enters the G-cloud in approximately 50,000 years, the denser interstellar material will compress the bow wave further. The solar system will have a more pronounced bow wave, more tightly compressed. The transition to the interstellar medium will be sharper. The protective effect might increase or decrease, depending on the specific conditions. Understanding the bow wave helps us understand stellar motion through the galaxy. Every star leaves a wake. Every star creates a structure in the interstellar medium. These structures reveal the motion of stars and their interactions with the galaxy. They're like trails in the snow, showing the path each star has taken. 23. It takes 300 years for an object to exit completely from the solar system. How long does it take for something to leave the solar system? The answer depends on what you mean by leave. If you mean crossing the heliopause for Voyager 1, it took 35 years. But if you mean completely escaping the solar system's gravitational influence, exiting the Oort cloud entirely, then the answer is dramatically different. It takes approximately 300 years for an object traveling at Voyager's speed to traverse the Oort cloud and leave the solar system behind completely. Voyager 1 is currently traveling at approximately 17 kilometers per second relative to the Sun. This is fast by spacecraft standards, but slow by astronomical standards. At this velocity, it would take about 70,000 years for Voyager 1 to reach the outer edge of the Oort cloud if it were aimed directly toward it. But Voyager isn't aimed in any particular direction toward the cloud. It's headed toward a specific part of the sky, which happens to be roughly tangential to the Oort cloud's expanse. The Oort cloud has a minimum radius of about 2,000 astronomical units, extending to a maximum of perhaps 100,000 astronomical units. One astronomical unit is the Earth-Sun distance, about 150 million kilometers. So the minimum distance is about 300 billion kilometers. The maximum is about 15 trillion kilometers. These are staggering distances. If an object were placed at the inner edge of the Oort cloud with zero initial velocity, it would take roughly 300 years to fall through the entire cloud and reach interstellar space. This is derived from gravitational calculations. The Sun's gravity, though weak at these distances, still accelerates objects inward. The acceleration is tiny, only about 0.001 meters per second squared, but it's constant. Over centuries it adds up. However, if an object is already moving at Voyager's speed, the calculation changes. Voyager is moving fast enough that it doesn't significantly fall inward. It travels roughly radially outward from the Sun. But its trajectory passes through the Oort cloud, so it will encounter objects along the way. The time it spends within the cloud depends on its exact trajectory. If Voyager were placed at the inner edge of the Oort cloud and instructed to exit it as quickly as possible, it would take about 30,000 years to traverse the cloud completely. This assumes a direct trajectory outward and no gravitational interaction with objects along the way. In reality, individual Oort cloud objects might deflect Voyager slightly, prolonging the journey marginally. The 300-year figure comes from a different calculation. It considers an object starting from rest at some distance from the Sun and falling radially inward through the Oort cloud. The time it takes depends on the starting point. Farther objects take longer to fall inward. But for a typical object falling from a typical Oort cloud distance, 300 years is a reasonable estimate for the time spent within the cloud. This calculation reveals something profound. The Oort cloud is thick. It's not a thin shell, but a substantial region of space. Objects within it take centuries to traverse. Even traveling at Voyager's speed, exiting the cloud completely would require tens of thousands of years. The thickness of the Oort cloud also means that comets can spend an extraordinarily long time within it. If a comet is perturbed by a passing star and begins falling inward toward the Sun, it might take thousands of years to reach the inner solar system. During this time, it's constantly accelerating under the Sun's gravity. By the time it reaches the inner solar system, it's traveling at tremendous speed, perhaps tens of kilometers per second. This is why long-period comets are so fast and so impressive when they reach the inner solar system. They've had thousands of years to accelerate. The gravitational potential energy of the distant Oort cloud is converted to kinetic energy as they fall inward. It's like objects rolling down a very long, shallow hill. The 300-year estimate also has implications for the stability of the Oort cloud. Objects within it are relatively stable for billions of years. They won't spontaneously escape or fall into the Sun. They'll remain in their orbits unless something disturbs them. The only significant perturbations are from passing stars or the galactic tides. Understanding the time scale for exiting the Oort cloud helps us understand the long-term future of the solar system. In billions of years, as the solar system ages and the Sun begins to evolve, the Oort cloud will remain relatively unchanged. It will preserve its objects for future eons. Only when the sun finally dies will the Oort cloud truly be freed from its gravitational bonds. For now, Voyager 1 is on its journey through the Oort cloud. If it could remain functional for tens of thousands of years, it would eventually emerge on the other side. But more likely, it will go silent long before that, drifting silently through the dark expanse, carrying humanity's message into the depths of the cosmos. 24. Dust from interstellar space can enter the solar system. The solar system is not isolated from the interstellar medium. Dust particles from space can penetrate the heliopause and enter the solar system. These particles travel vast distances between stars before entering our planetary system. Some come from nearby supernova remnants. Others come from dust clouds surrounding other stars. Some are ancient particles that have been traveling through space for billions of years. The detection of interstellar dust was one of the surprising discoveries made by spacecraft that left the solar system. The Voyagers detected it. More recently, sophisticated instruments on the New Horizons spacecraft detected it as well. The dust particles are typically tiny, ranging from nanometers to micrometers in size. But despite their size, they carry significant information about the interstellar medium. Interstellar dust is composed primarily of silicates and carbonaceous materials. These are the same types of materials found in meteorites that fall to Earth. The dust is created through various processes: grinding of larger particles in supernova explosions, condensation around cool stars, and chemical reactions in interstellar clouds. Each dust grain is like a fossil, carrying a record of its origin. The flux of interstellar dust entering the solar system is surprisingly high. Scientists estimate that approximately 40,000 kilograms of interstellar dust enter the solar system every year. That sounds like a lot, but spread over the entire inner solar system, it's incredibly dilute. Still, the cumulative effect over time is significant. Some of this dust reaches Earth. Micrometeorites constantly rain down on our planet. Scientists have recovered dust from the stratosphere that has interstellar origin. By analyzing the composition and isotopic ratios, they can determine that this material came from outside the solar system. It's genuine cosmic dust. The interstellar dust follows a specific trajectory through the solar system. It enters primarily from one direction, the direction opposite to the solar system's motion through the galaxy. As the solar system moves through space, it pushes ahead of itself, like a car driving through fog. The dust in front has nowhere to go but gets pushed aside or swallowed. The dust from behind enters the wake created by the solar system's motion. This asymmetry is observable. Spacecraft detect more interstellar dust coming from one direction than another. The distribution matches theoretical predictions based on the solar system's motion through the galaxy. It's further confirmation that we're moving through space, and that the interstellar medium is responding to our passage. The entry of interstellar dust has implications for planetary protection. Some scientists worry that this dust could carry microbes from other star systems. If life exists around other stars, and if some of that life is small enough to be carried by dust particles, then interstellar dust could be a vector for panspermia, the transfer of life between star systems. However, the harsh conditions in space, radiation, extreme cold, desiccation, probably kill most potential microbes. Still, it's theoretically possible. The dust also has implications for climate. On very long timescales, variations in the flux of interstellar dust entering the solar system could affect Earth's climate. More dust would increase the albedo of the upper atmosphere, potentially cooling the planet. Less dust would have the opposite effect. However, this effect is probably minor compared to other factors affecting climate. The composition of interstellar dust reveals information about stellar nucleosynthesis and supernova processes. Different types of dust are created by different types of stars or explosions. By collecting and analyzing the dust, scientists learn about the processes occurring across the galaxy. Interstellar dust is a sample of galactic material delivered directly to us by cosmic processes. Scientists have also proposed using interstellar dust as a means to detect exotic particles. Some theoretical physics suggests the existence of particles that interact only gravitationally, like WIMPs, weakly interacting massive particles. These particles might interact with interstellar dust in subtle ways. By analyzing dust collected from space, scientists might detect evidence of these particles. It's a clever use of naturally occurring material to test exotic physics. The Stardust spacecraft, which returned from Comet Wild 2 in 2006, captured interstellar dust particles using aerogel, a lightweight foam material. The particles were preserved perfectly in the foam, allowing detailed analysis. Some of the dust proved to be definitively interstellar in origin. The mission demonstrated that it's possible to collect and analyze such particles, opening new possibilities for understanding the interstellar medium. As the solar system moves through different regions of the galaxy, the composition of infalling interstellar dust might change. When the solar system enters the G-cloud, the dust will be different. Scientists studying modern interstellar dust are effectively studying a snapshot of the galaxy at this moment in time. In thousands of years, that snapshot will have changed, but the dust preserved in Earth's stratosphere will remain as a record. 25. We are currently passing through an interstellar cloud. The local interstellar cloud is a region of relatively low-density interstellar material where the Sun currently resides. It's sometimes called the local fluff, a name that seems whimsical but is used seriously in astronomical literature. The cloud is roughly 30 light-years across and has a density of only about 0.3 particles per cubic centimeter, which is about 10,000 times less dense than Earth's atmosphere at sea level. Yet by interstellar standards, it's relatively thick. The local interstellar cloud formed from the remnants of one or more supernova explosions several million years ago. When massive stars explode, they scatter material across space. This material cools and collects into clouds. The local interstellar cloud is such a remnant, perhaps enhanced by material from multiple explosions or shaped by multiple stellar wind interactions. The Sun entered the local interstellar cloud approximately 50,000 years ago and will remain within it for roughly the next 50,000 years. This period is significant in the context of solar system history. For most of its 4.6 billion-year existence, the Sun has been moving through various interstellar regions, but only recently has it been within the relatively calm local fluff. The local interstellar cloud is expanding. Its boundaries are moving outward as the material disperses due to the pressure of nearby stellar winds and the cosmic rays from supernovae. The Sun is currently near one edge of the cloud. In tens of thousands of years, it will exit and enter a different region of space. Currently, the solar system is not significantly affected by being within the local interstellar cloud. The cloud is too dilute to compress the heliopause substantially. The cosmic ray flux is normal. The interstellar dust influx is manageable. We're in a relatively benign environment. But this is temporary. The Voyagers have provided direct samples of the local interstellar cloud material. By analyzing the composition and properties of the plasma they encounter, scientists can determine the cloud's characteristics. The data confirms theoretical predictions about the cloud's density, temperature, and composition. Near the boundary of the local interstellar cloud lie other clouds. The G cloud, or Gould's Belt extension, is approaching. In about 50,000 years, the solar system will begin entering the G cloud, a much denser region of interstellar material. When that happens, conditions will change dramatically. The local interstellar cloud provides a protective environment compared to the average galactic neighborhood. Most of space between stars is much denser and more hostile. Denser regions have higher cosmic ray fluxes and more material to compress the heliopause. The Sun is fortunate to currently be in a relatively protected region. Different regions of the local interstellar cloud have slightly different properties. The Sun is currently moving through one region and will eventually transition to another. These transitions are usually gradual, occurring over hundreds or thousands of years. But as boundaries approach, changes become noticeable. The local interstellar cloud is also interesting because it contains within it a region called the G cloud, or Gould's Belt. This is a structure of dense gas and star-forming regions that spans about 600 light-years. The local fluff is embedded within or adjacent to this larger structure. In a sense, the local interstellar cloud is a small component of a larger interstellar landscape. Stars other than the Sun also reside within the local interstellar cloud. Proxima Centauri, the nearest star, is also within it. Sirius and several other nearby stars are as well. These stars are neighbors in the same cloud, though separated by light-years of distance. The fact that the Sun is in the local interstellar cloud is somewhat fortunate. The cloud's low density protects Earth from excessive cosmic ray exposure. If the Sun were in a denser cloud, more cosmic rays would reach Earth. This would increase radiation exposure and potentially increase mutation rates and cancer in terrestrial life. The local fluff is literally protecting us. As humanity becomes increasingly sophisticated, the knowledge that we're passing through an interstellar cloud becomes more meaningful. We're not stationary. We're moving through the galaxy. The environment around us is changing on timescales of tens of thousands of years. This gives perspective to human civilization, which has existed for only a few million years. We're living during a particular, temporary phase in the solar system's journey. 26. The next star system is 4.2 light-years away. Proxima Centauri is the nearest star to the Sun. It's located 4.24 light-years away, or about 40 trillion kilometers. Light from the Sun takes approximately 8 minutes to reach Earth, but light from Proxima Centauri takes over 4 years to reach us. This enormous distance demonstrates the isolation of stars from each other. Proxima Centauri is a red dwarf star, much smaller and dimmer than the Sun. Its mass is only about 0.12 times the Sun's mass. Its luminosity is less than 0.01 times the Sun's luminosity. If you were to stand at the same distance from Proxima Centauri as Earth is from the Sun, Proxima would provide only about 1% of the light and heat that Earth currently receives from our Sun. The surface of Proxima is cooler, around 3,000 Kelvin, compared to the Sun's 5,800 Kelvin. Despite being small and dim, Proxima Centauri is interesting because it hosts at least 2 planets. One planet, called Proxima Centauri b, is in the habitable zone. It receives enough heat from its star to potentially have liquid water. This is remarkable. The nearest star system contains a potentially habitable world. If life exists elsewhere, this would be the closest place to look. Proxima Centauri is actually part of a triple star system. Along with Proxima, there are 2 brighter stars called Alpha Centauri A and Alpha Centauri b. These 2 are roughly 2.2 light-years beyond Proxima, taking them to about 6.4 light-years from the Sun. The 3 stars are gravitationally bound to each other, forming a system. The distance to Proxima Centauri means that communication with any probe sent there would take enormous time. A signal traveling at the speed of light takes 4.24 years to arrive. A response takes another 4.24 years. Any real-time communication is impossible. Commands must be sent years in advance. Sending a probe to Proxima Centauri is theoretically possible, but practically very difficult with current technology. The fastest spacecraft, Voyager 1, traveling at 17 kilometers per second, would take over 70,000 years to reach Proxima. That's roughly 400 times longer than human civilization has existed. Even hypothetical spacecraft traveling at 10% the speed of light would take over 40 years to reach Proxima. But theoretically advanced civilizations might have accomplished this journey. Directed energy or interstellar sails could potentially accelerate a probe to much higher speeds. A civilization with such technology could traverse the distance to Proxima in decades or centuries. The fact that we haven't detected signals from such probes suggests that no such civilization has sent them, or if they have, we don't know how to recognize the signals. The distance to Proxima also means that the two star systems are gravitationally independent. The Sun's gravity doesn't significantly affect Proxima's planets, and vice versa. Yet they're still the closest neighbors in a vast galaxy. If these are the closest neighbors in this particular region, the distances between star systems are truly astronomical. The Oort cloud is much farther. Its outer edge approaches 2 light-years from the Sun, getting closer to Proxima Centauri than the Sun itself is in some directions. In other directions, it extends beyond 2 light-years. So the Oort cloud actually overlaps with the region nearest to Proxima Centauri. This means objects from our Oort cloud might be closer to Proxima than to the Sun. The arrangement is interesting. Our solar system's Oort cloud and Proxima's habitable zone are not that far apart on galactic scales. But even so, the distance is staggering. It would take tens of thousands of years for a comet from our Oort cloud to reach the Proxima system. In the distant future, the solar system will move through the galaxy. Eventually, some other star will be at the position where Proxima currently is. The nearest star won't always be Proxima Centauri. In millions of years, it might be some other star. The identity of the nearest neighbor changes slowly over time. For now, Proxima Centauri is our nearest neighbor. It's the closest place where a different sun shines. It's the first rung on the ladder reaching out to the galaxy. And the distance of 4.24 light-years represents a fundamental truth about the universe. The stars are isolated, separated by immense voids, connected only by gravity and the memory of past proximity. 27. The solar system moves at 800,000 kilometers h. Through the galaxy, the Sun isn't stationary, neither is any star. The entire solar system is hurtling through space at approximately 220 kilometers per second relative to the galactic center. That's 792,000 kilometers per hour, or roughly 2% the speed of light. This isn't the solar system's motion through the local interstellar cloud, which is much slower. This is the motion of everything, the Sun, Earth, all the planets, orbiting the center of the Milky Way galaxy. The Sun takes approximately 225 to 250 million years to complete one full orbit around the galactic center. This period is sometimes called a galactic year or cosmic year. It's a unit of time that puts Earth's history in perspective. Dinosaurs roamed Earth the last time the solar system was in this position relative to the galactic center. The continents were arranged differently. The stars were in different positions. Everything has changed since then. The Sun's orbit around the galaxy is not circular. It's elliptical, like planetary orbits around the Sun, but on a much larger scale. The solar system travels closer to the galactic center at some points in its orbit, and farther away at others. Currently, the solar system is not at the closest point to the galactic center. It's somewhere in the middle of its orbit, having been moving outward for some time. The geometry of this motion is complex. The Sun orbits the galactic center, but it also bobs up and down through the galactic plane. The Sun oscillates above and below the plane with a period of about 60 to 80 million years. This means the Sun spends part of its time above the galactic disk and part below. Currently, the Sun is above the plane and moving downward. It will cross the plane in a few million years. This vertical oscillation has implications for Earth's history. When the solar system crosses the galactic plane, it passes through regions with higher density of dust and gas. This can increase the number of comets deflected into the inner solar system. Some scientists have proposed that mass extinction events on Earth correlate with the solar system's passage through the galactic plane, though this remains controversial. The solar system's motion through the galaxy is driven by the gravitational attraction of all the mass in the galaxy. The Sun doesn't orbit a single central point. Instead, it orbits the collective gravity of hundreds of billions of stars, plus gas, dust, and dark matter. Dark matter is particularly important. It comprises most of the galaxy's mass, though we can't see it directly. Its gravity dominates the motion of stars and gas. The velocity of 220 kilometers per second is not absolute. It's relative to the galactic center. The solar system also has motion relative to the local interstellar cloud, which is about 25 kilometers per second. It also has motion relative to the cosmic microwave background radiation, the afterglow of the Big Bang. Each reference frame gives a different velocity. Velocity is always relative. The motion through the galaxy affects the solar system's interaction with the interstellar medium. As the solar system moves, it encounters different densities and compositions of gas and dust. It creates the bow wave and heliotail discussed earlier. The structure of the solar system is constantly being shaped by this motion through the galaxy. Different stars have different orbital velocities through the galaxy. Young stars in star-forming regions typically move slower, around 100 to 150 kilometers per second. Older stars in globular clusters move faster, sometimes over 300 kilometers per second. The Sun, at 220 kilometers per second, is moving at a moderate speed. This suggests it formed with other stars moving at similar speeds, possibly in a cluster that has since dispersed. The Sun's path through the galaxy is not predetermined. While its current motion carries it on a predictable orbit, perturbations from passing stars and gravitational irregularities can alter its trajectory over billions of years. Over timescales of billions of years, small changes accumulate. Eventually, the solar system's orbit might be significantly different from what we predict. The passage through the galaxy also brings the solar system closer to and farther from different types of stellar nurseries and supernova remnants. When the solar system is in a region with many massive stars, it experiences higher cosmic ray fluxes and more frequent stellar winds. When it's in a quieter region, conditions are more benign. The environment is constantly changing. One consequence of this motion is that Earth's climate is not determined only by factors within the solar system. Events in the broader galaxy can affect Earth. A nearby supernova could bathe Earth in radiation. A stellar encounter could deflect Oort cloud objects into the inner solar system. The solar system is not isolated. It's embedded in the galactic environment, constantly interacting with it. Understanding the solar system's motion through the galaxy gives perspective on our place in the cosmos. We're not stationary. We're in motion, and this motion will continue for billions of years, taking us through different regions of the galaxy, encountering different conditions, and exposing Earth to different cosmic environments. 28. the solar system will enter another interstellar cloud in 50,000 years. In approximately 50,000 years, the solar system will exit the local interstellar cloud and enter a much denser region called the G cloud, or Gould's Belt extension. This transition will be significant. The conditions around Earth will change. The cosmic ray flux will increase. The interstellar dust influx will increase. The heliopause will compress. None of these changes will immediately threaten Earth's biosphere, but they will alter the environment significantly. The G cloud is roughly 10 times denser than the local interstellar cloud. Its density is estimated at about 3 particles per cubic centimeter, still incredibly dilute by terrestrial standards, but substantial by interstellar measures. The increased density means increased pressure on the heliopause. The solar system's protective bubble will shrink. When the heliopause compresses, the cosmic ray flux at Earth will increase. Cosmic rays are currently suppressed by a factor of about 1,000 due to the combined effect of the heliopause and Earth's magnetosphere. When the heliopause compresses, this suppression factor decreases. The cosmic ray flux at Earth's surface could increase by perhaps 50% to 100%, depending on exactly how much the heliopause compresses. An increase in cosmic ray flux has biological implications. Cosmic rays damage DNA. They cause mutations. They increase cancer rates. For organisms protected by a strong magnetosphere, like those on Earth, the effect is mild. But for organisms in upper atmosphere or in spacecraft, the effect could be more severe. Long-term space missions would be more hazardous. The increased dust influx is another consequence. As the density of the G cloud increases, so does the flux of dust particles entering the solar system. More meteorites would reach Earth's atmosphere. More material would be deposited in the upper atmosphere. This could have subtle effects on climate by changing the albedo of the atmosphere slightly. The increased density also means the bow shock becomes more pronounced. The heliotail becomes more compressed and structured. The solar system becomes more clearly delineated against the surrounding interstellar medium. From the perspective of an outside observer, the solar system would become more visible, more distinct against the background. The transition into the G cloud will not happen suddenly. It will take place over thousands of years. The density will gradually increase. The heliopause will gradually shrink. Changes will be incremental. There will be no single moment when everything changes. Instead, conditions will drift gradually from the current state to the new state. Scientists know about the G cloud's approach from astronomical observations. By mapping the density and velocity of gas in the galactic neighborhood, astronomers can predict where the solar system will go. The solar system's trajectory through space is well understood. Its collision course with the G cloud is inevitable, barring some unexpected perturbation. The duration of the solar system's stay in the G cloud is unclear. The G cloud is itself moving through space. Its position and shape are changing slowly. The solar system will eventually exit it and enter yet another region of the galactic neighborhood. But this exit might not occur for hundreds of thousands of years or millions of years. The timescale depends on the velocities and positions of both the solar system and the G cloud. When the solar system eventually exits the G cloud, it will enter some other region of space. The properties of that region are unknown. It might be denser than the G cloud. It might be less dense. It might have different temperature and composition. The galactic environment is variable. No two regions are identical. This raises an interesting question. What was the galactic environment like the last time the solar system was in a similar position in its orbit? The answer depends on how much things have changed in 225 to 250 million years. Stars move, clouds dissipate and reform. The galactic neighborhood is dynamic. The environment 225 million years ago was certainly different from today. The eventual passage through the G-cloud is just one event in the solar system's long history. Over billions of years, it will pass through dozens or hundreds of different interstellar clouds. Each passage will alter conditions around Earth. Each passage will potentially affect the evolution of life. The G-cloud passage is significant, but it's one moment among many in the solar system's galactic journey. For now, the G-cloud lies in the future, but its approach is inevitable. In tens of thousands of years, if humanity or its descendants still exist, they will witness the beginning of the transition. They will observe increasing cosmic ray fluxes. They will measure increasing dust influx. They will detect the gradual compression of the heliopause. They will witness a fundamental change in the galactic environment around the solar system. 29. Some objects orbit the Sun backward. Most objects in the solar system orbit the Sun in the same direction, counterclockwise when viewed from above Earth's north pole. This is called prograde motion. The planets orbit this way. Most asteroids orbit this way. Most comets orbit this way. But some objects orbit the Sun in the opposite direction. This is called retrograde motion. These objects are rare, but they exist. Retrograde orbits raise questions. How did these objects acquire their backward orbits? What does it tell us about the solar system's history? The answers involve gravitational interactions and events billions of years ago. Most retrograde objects were likely captured from interstellar space or from other systems. A few were likely ejected into retrograde orbits by interactions with other objects. One of the most famous retrograde objects is Halley's Comet. It orbits the Sun with a retrograde trajectory, approaching the inner solar system every 75 to 76 years. Its orbit is tilted at about 162 degrees relative to the ecliptic plane, meaning it orbits nearly backward. Halley's Comet is thought to have been captured into this orbit millions of years ago by gravitational interactions with Jupiter and Saturn. Another notable retrograde object is the asteroid 2461 Sarabhai, discovered in 996. It has a retrograde orbit with a period of about 3.3 years. Many other smaller asteroids have retrograde orbits as well. The exact number is hard to determine because faint asteroids are difficult to detect, especially if their orbits take them far from the ecliptic plane. Retrograde comets are thought to come from the Oort cloud. When a comet is perturbed and begins falling toward the Sun, it approaches from a random direction. Some approach from directions that result in retrograde orbits around the Sun. These comets are captured into temporary retrograde orbits, orbit the Sun one or more times, and eventually return to interstellar space or are ejected from the solar system. The capture mechanism involves the gravitational influence of the giant planets, particularly Jupiter. Jupiter is massive enough to significantly alter the trajectory of a passing comet. If a comet approaches from the right direction, Jupiter's gravity can flip its trajectory, making it orbit backward relative to the solar system's general motion. Long-period comets often have retrograde orbits because they haven't been in the solar system long enough to be perturbed into prograde orbits. They haven't had multiple close encounters with Jupiter that would gradually align their orbits. They're recent visitors from the Oort cloud, still carrying signatures of their origin. Some retrograde objects might be interlopers from other star systems. Rogue planets or comets ejected from their native star systems might occasionally wander into the solar system. An object from another system would have a random inclination and could easily be retrograde. Detecting such interlopers is challenging because they're rare and difficult to distinguish from solar system objects. The existence of retrograde objects is valuable for understanding the solar system's history and current dynamics. They provide clues about the interactions occurring billions of years ago. They demonstrate that the solar system is not perfectly orderly. There's chaos and complexity underneath the apparent regularity. Retrograde orbits are not stable forever. A retrograde object might collide with a prograde object. It might be captured into a prograde orbit through gravitational interactions. It might be ejected from the solar system. Eventually, most retrograde objects are removed through one mechanism or another. The fact that some still exist suggests they're recent additions, or that the solar system is still actively capturing new objects. The stability of retrograde orbits depends on the object's location and the specific dynamics of the region. In the inner solar system, retrograde orbits are relatively unstable. Objects are frequently perturbed. In the outer solar system and beyond, retrograde orbits can be more stable. Objects can persist in retrograde orbits for millions or billions of years if undisturbed. One fascinating aspect is that retrograde orbits affect how we detect exoplanets around other stars. Some exoplanets have been discovered to have retrograde orbits around their host stars. This suggests they were captured from other systems or were scattered by gravitational interactions with other planets. Understanding retrograde orbits in our solar system helps us interpret observations of exoplanetary systems. Retrograde objects also have implications for planetary protection and spacecraft missions. A probe in a retrograde orbit has a different velocity relative to objects in prograde orbits. Collisions between the two would be particularly violent due to the high relative velocity. Trajectory planning for missions to asteroids or comets must account for the object's orbital direction. 30. The Oort cloud will enter. Another interstellar cloud in 50,000 years. The passage of the solar system into the G cloud doesn't happen all at once to the entire system. The boundary of the G cloud will first encounter the outer regions of the solar system. The Oort cloud, extending far beyond the Kuiper belt, will be affected before the inner solar system is. This means the Oort cloud will enter the G cloud approximately 50,000 years before the heliopause does. When the outer Oort cloud encounters the higher density of the G cloud, several things occur. The pressure increases. Dust and gas begin to accumulate. The boundary between the Oort cloud and the interstellar medium becomes less distinct. The G-cloud material begins to penetrate the outermost regions of the Oort cloud. This has implications for comets. Objects in the outer Oort cloud that were barely bound to the solar system might be pulled away by the gravity of G-cloud material. If a small star or a particularly massive gas clump passes through the Oort cloud, its gravity could scatter Oort cloud objects. Some might be captured by this external object. Others might be ejected entirely. The comets that become unbound during this passage would become interstellar objects. They would drift away from the solar system, eventually reaching another star system or drifting eternally between the stars. It's possible that some of Earth's ancient bombardment of comets came from the solar system's previous passages through denser regions. Objects ejected then might eventually return if the solar system passes through similar regions again. The increased density of material might also affect the structure of the Oort cloud. The Oort cloud's current shape is influenced by the solar system's motion through the local interstellar cloud. When the solar system enters the G cloud, the asymmetrical pressure will create a different shape. The Oort cloud will be compressed on one side and extended on the other, reflecting the pressure gradient of the surrounding interstellar medium. Another effect is on the long-period comets. When a long-period comet is perturbed and begins falling toward the inner solar system, it gains speed due to the Sun's gravity. Its trajectory is determined by the initial perturbation. If the perturbation is stronger, due to the denser environment, more comets might be scattered from the Oort cloud. The flux of long-period comets into the inner solar system might increase. This increased comet flux would have been noticeable during Earth's geological history. If the solar system passed through dense regions in the past, ancient rock records might show evidence of increased cosmic impacts. Crater densities on the Moon could reflect these events. Indeed, some astronomers have proposed that mass extinctions and increased impact rates correlate with the solar system's position in the galaxy. The timescale of 50,000 years is significant in human terms, but trivial in astronomical terms. To the Oort cloud, it's an instant. But to human civilization, it's enough time for dramatic changes. In 50,000 years, humanity might have advanced technologically in ways we can't predict. We might have established outposts throughout the solar system. We might have sent interstellar probes. We might have fundamentally changed society. Understanding that the solar system will enter a denser region helps us appreciate the variability of galactic conditions. The environment around Earth is not constant. It changes. These changes occur on timescales of tens of thousands of years, far longer than human civilization has existed. But they're brief compared to the age of the solar system. The passage through the G cloud will eventually end. The solar system will exit the cloud and enter some other region. The next several 100,000 years will see the solar system moving through various interstellar clouds. Each passage will add a chapter to the solar system's story. Each will affect conditions on Earth in subtle ways. 31. Astronomers discover invisible objects in total darkness. How do astronomers find objects that are too dark to see? The short answer is indirectly. They observe the effects the objects have on other things. This technique has proven invaluable for discovering distant, faint objects at the edge of the solar system. The most famous example is how Pluto was discovered in 1930, and how Eris was discovered in 2005. Pluto was discovered because it was thought to be affecting the orbits of Neptune and Uranus. Astronomers noticed small inconsistencies in the predicted positions of these planets. They hypothesized an unseen object causing the perturbations. Using the predicted position, Clyde Tombaugh was able to identify Pluto on photographic plates. It turned out the perturbations were actually due to errors in earlier mass estimates, and Pluto wasn't the culprit. But the indirect method worked anyway. Eris was discovered using a different indirect method. Astronomers were cataloging distant objects in the Kuiper belt. By imaging the same region of sky at different times and looking for objects that moved, they could detect new objects. The motion revealed the object's presence, even if the object itself was too faint to identify definitively. Eris was detected this way, then followed up with more detailed observations to confirm its existence and measure its properties. The Gaia spacecraft has revolutionized indirect detection. By measuring the positions of billions of stars extremely precisely, Gaia can detect perturbations in their motions caused by unseen objects. A massive object like the planet 9 would gravitationally tug on nearby stars, causing tiny wobbles in their positions. Analyzing these wobbles could reveal the presence of the unseen object, even if it's not directly observable. Gravitational lensing is another indirect method. Massive objects bend space-time, and light bends as it passes through curved space-time. If a faint object is positioned behind a bright object, the light from the bright object can be bent by the faint object's gravity. This creates a magnified or distorted image. By analyzing the distortion, astronomers can infer the presence and mass of the unseen object. Infrared and ultraviolet observations can reveal objects invisible to optical telescopes. Objects that are too dark in visible light might still emit infrared radiation if they're warm enough, or they might reflect ultraviolet light from nearby stars. Different wavelengths reveal different aspects of objects. Some objects that are invisible in one wavelength are bright in another. Radio observations can detect objects that emit radio waves. Some objects, like neutron stars or active galactic nuclei, produce radio waves that can be detected across vast distances. By listening for these signals, astronomers can identify unseen objects. The technique is similar to detecting aircraft at night using radar instead of looking with eyes. X-ray observations can detect extremely hot or extremely energetic objects, neutron stars, black holes, and objects in violent collisions emit X-rays. By searching for X-ray sources, astronomers can identify objects that would be completely invisible in optical light. Some of the most violent events in the universe are first discovered as X-ray flashes. Gravitational wave astronomy has opened entirely new possibilities. Gravitational waves are ripples in space-time itself, created by accelerating massive objects. A merger of two neutron stars or black holes creates gravitational waves that propagate across the universe. By detecting these waves, astronomers can identify events invisible by any other method. Objects billions of light-years away can be detected through gravitational waves. The solar system is filled with objects we can't see directly. The Oort cloud contains trillions of objects, and we've never directly observed a single one. We know it exists because of the comets that fall from it. The atmosphere of Jupiter's moons, some of them, were detected through indirect methods before being confirmed through direct observation or detailed study. Future technology will improve indirect detection. More sensitive instruments will detect fainter objects. Better algorithms will identify subtle perturbations. Advanced artificial intelligence might recognize patterns in data that humans miss. Gravitational wave observatories will improve in sensitivity. Radio telescopes will become more powerful. All of this will enable the discovery of fainter, more distant, and more exotic objects. The lesson is that the universe is full of invisible objects. Invisibility doesn't mean non-existence. Clever observation and analysis can reveal what direct vision cannot. The solar system's edge is populated with objects we don't see, but which we know are there, and future discoveries will likely reveal even more of the hidden structure of the solar system and the galaxy beyond. 32. What happens if you traveled beyond the edge? Imagine traveling beyond the solar system's edge into the interstellar medium. What would you experience? The journey would be extraordinary, filled with environments humans have never encountered. The transition from the solar system to interstellar space is gradual. There's no boundary you cross where suddenly everything changes. Instead, conditions shift gradually. If you were traveling outward from the sun, you'd first pass through the planets and their various orbital zones. The Kuiper Belt would come next, filled with frozen dwarf planets and comets. You'd encounter Pluto, Eris, and countless other icy worlds. The light from the sun would gradually dim. At Pluto's distance, the sun appears as a bright star, not as the dominant light source it seems from Earth. Continuing outward, you'd enter the scattered disk, where objects have even more eccentric orbits. Then comes the long journey through the near-empty region between the scattered disk and the Oort cloud. For years or decades, depending on your speed, you'd see nothing but stars and the occasional comet nucleus. The sun would become just another point of light in the sky. Upon reaching the Oort cloud, you'd begin encountering the trillions of comets. Each one would be a small world, kilometers across, covered in frozen volatiles. If you could somehow visit a few of them, you'd find they're not uniform. Some are darker, covered in dark materials. Some are brighter, with fresh frost. Their compositions vary. As you traveled through the Oort cloud, the density of objects would gradually increase as you got closer to the inner edge, then decrease as you moved toward the outer edge. The journey through the entire cloud, if you passed through the center, could take hundreds of years at Voyager speeds. At higher speeds, perhaps decades or centuries. Finally, crossing the heliopause, you'd detect an immediate change. The magnetic field would flip direction. The particle density would change. You'd be in the heliosheath, between the heliopause and the termination shock. Here, the solar wind is being decelerated. The temperature is millions of degrees. Radiation is intense. Crossing the termination shock would bring another dramatic change. The temperature would spike, the density would increase. The magnetic field would become more complex. You'd have officially left the solar system in any conventional sense. Beyond that lies the interstellar medium. The temperature would gradually decrease as you moved away from the heliopause. The density would fluctuate as you passed through different regions. If you were heading toward Proxima Centauri, after 40,000 years of travel, you'd begin approaching that stellar system. What would you bring with you for such a journey? Life support for decades or centuries, instruments to measure the environment, a power source to maintain your systems, propulsion to accelerate to high speeds. The journey would be lonely. Other stars are so far away that passing another spacecraft would be extraordinarily unlikely. What would you find valuable to study? The composition of the interstellar medium, the strength and direction of the interstellar magnetic field, the cosmic ray environment, the distribution of dust, the structure of the heliopause and how it varies, the properties of Oort cloud objects. All of this data would be invaluable for science. The psychological experience would be profound. As the sun receded from bright beacon to dim point of light, to invisible presence, you'd be isolated in a way few humans have ever been. You'd be beyond the reach of human civilization. Your journey would take longer than human history to complete. You'd be a pioneer of the deepest kind. Perhaps in the distant future, when human technology has advanced far beyond current capabilities, such journeys will be possible. Robots might explore the interstellar medium, gathering data and transmitting it back across the vast distances. Future humans might travel these routes themselves, driven by curiosity and the desire to explore. For now, we must be content with the Voyager's journeys. These remote spacecraft serve as our emissaries, traveling into the unknown, gathering data about the regions beyond. Their continued operation, even as their power declines, keeps this frontier of exploration active. They represent humanity's commitment to understanding the universe, no matter how distant or hostile the environment. 33. The most distant objects take millions of years to be discovered. Finding objects at the edge of the solar system is extraordinarily challenging. The farthest objects are so distant and so faint that they might take millions of years to be discovered, even with modern telescopes. Some objects are so far away that they won't reflect enough light for detection until our technology advances far beyond current capabilities. Others might never be discovered, remaining hidden in the darkness for billions of years. The problem is fundamental to astronomy. Faint objects are hard to see. An object's brightness decreases with the square of its distance. An object twice as far away appears 4 times dimmer. An object 10 times farther appears 100 times dimmer. At the distances of the outer Oort cloud, objects are so faint that even the largest telescopes struggle to detect them. Most remain invisible. Current surveys like Pan-STARRS and the upcoming Vera C. Rubin Observatory have dramatically improved our ability to find distant objects, but they can only detect down to a certain magnitude limit. Objects fainter than that limit remain undetected, no matter how large they are. There could be Pluto-sized objects orbiting beyond Sedna that we've never seen simply because they're too faint. The discovery rate of Kuiper Belt objects has accelerated dramatically over the past 25 years. In the 1990s, astronomers discovered a handful of objects per year. By the 2020s, the rate had increased to dozens per year. As survey technology improves, the discovery rate will continue to increase. But there are limits. Eventually, we'll have discovered all the bright objects. The remaining objects will be progressively fainter and take longer to find. Statistically, astronomers estimate there are hundreds of thousands of Kuiper Belt objects with diameters larger than 100 kilometers. Only about 3% have been discovered as of 2025. That means 97% remain unknown. Each year, new discoveries add to our catalogue. But at current rates, it would take centuries to discover all the major objects. The situation is even more extreme for the Oort cloud. We've never directly observed a single Oort cloud object. We know it exists because comets fall from it. We can estimate its properties based on theoretical models and comet observations. But direct detection of Oort cloud objects is beyond current capabilities. They're simply too far away and too faint. Future space telescopes might change this. A space-based infrared observatory could detect objects that emit infrared radiation. Objects in the outer solar system are cold, but not zero temperature. They emit some infrared radiation. With sensitive enough detectors, this radiation could be detected from vast distances. Advanced future telescopes might enable discoveries that currently seem impossible. Another approach involves detecting the gravitational effects of massive objects. The Planet 9, if it exists, should be detectable through its gravitational influence on other objects. Advanced gravitational measurement techniques might reveal its presence, but even this requires careful observation and analysis of many objects' orbits. The discovery of Planet 9 would revolutionize our understanding. It would prove that major planetary bodies can hide in the solar system even with modern telescopes. It would suggest other large objects might also be hidden. It would change how we think about solar system completeness. We'd realize that our knowledge is still very incomplete. Technological advancement is the key to future discoveries. Better detectors, larger telescopes, more sensitive instruments, and improved algorithms will all contribute. Artificial intelligence trained to recognize subtle patterns might identify objects that human astronomers miss. Distributed computing might allow citizens to contribute to discovery efforts by analyzing data. Another factor is time. Some objects are at positions in their orbits where they're particularly dim. As they move, they'll become brighter. In decades or centuries, objects currently too faint to detect might become observable. Time brings new opportunities for discovery. The psychological aspect of undiscovered objects is profound. Right now, at this moment, there are likely hundreds or thousands of objects in the solar system that no human has ever detected or seen images of. They exist in complete darkness, unknown to anyone. They orbit the sun without recognition. Someday, explorers or automated systems will find them. They'll be mapped and catalogued and named. But until then, they remain secrets of the solar system. This reminds us of the vastness of space and our limited knowledge. Despite centuries of astronomy and decades of advanced space technology, we've only scratched the surface. The solar system contains multitudes that we've barely begun to comprehend, and this is just our local neighborhood. The galaxy contains billions of stars, each potentially with their own systems. The universe is profoundly larger and more complex than any individual human can fully grasp. 34. The solar system will enter. Another interstellar cloud in 50,000 years is an unfathomably long time from a human perspective. 50,000 years ago, humans were still in the Stone Age. Cave paintings were being created. Language was developing. Agriculture wouldn't begin for another 40,000 years. Writing wouldn't exist for another 48,000 years. 50,000 years encompasses all of recorded human history and then some. Yet, from an astronomical perspective, 50,000 years is merely an instant, and in exactly that instant, the solar system will undergo a significant transition. The G-cloud approaches. This denser region of interstellar material will engulf the solar system in approximately 50,000 years. The transition won't be sudden or catastrophic. The density will increase gradually over thousands of years, but the cumulative effect will be substantial. By the time the solar system has fully entered the G-cloud, conditions will be noticeably different from today. The first effects will be subtle. The cosmic ray flux will begin to increase slightly. The amount of interstellar dust reaching Earth will increase modestly. Astronomers monitoring the heliosphere will notice gradual changes in the boundary between the solar system and interstellar space. These changes will be measurable but not immediately alarming. As the solar system penetrates deeper into the G-cloud, the effects will become more pronounced. The heliopause will compress noticeably. The cosmic ray flux at Earth's surface could increase by 50% or more. The increase in cosmic ray exposure would trigger discussions among scientists about biological impacts. Some might argue for protective measures, though Earth's magnetosphere would still provide significant protection. The interstellar dust influx will increase dramatically. More meteorites will enter Earth's atmosphere. The upper atmosphere will accumulate more dust. This could have subtle effects on climate. Some models suggest that increased stratospheric dust could cool Earth slightly by reflecting incoming solar radiation. Other models suggest that the warming effect from increased atmospheric dust might be minor. The precise effect would depend on the specific composition and distribution of the dust. The bow shock will become more pronounced. The solar system will create a more distinct structure in the interstellar medium. The heliotail will become more compressed and more visible if observed from outside. The solar system will be more clearly delineated against its surroundings. From the perspective of a hypothetical observer far from the solar system, the change would be dramatic. The Oort cloud will experience the most dramatic changes. Objects at the outer edge of the cloud might be destabilized by the increased external pressure and density. Some might escape into interstellar space. Others might fall inward toward the sun. The flux of long-period comets entering the inner solar system could increase significantly during the transition period. If humanity or its descendants still exist in 50,000 years, they would witness this transition. They would observe it unfold. They would measure it with instruments far more advanced than anything we have today. The data collected would provide unprecedented insights into how stellar systems interact with interstellar environments. The passage through the G-cloud will eventually end. The solar system will exit this denser region and enter some other region of the galactic neighborhood. The duration of the stay in the G-cloud is uncertain. It might be only a few 100,000 years. It might be much longer. The exact timescale depends on the velocities and positions of both the solar system and the G-cloud. After leaving the G-cloud, the solar system will enter yet another region. The properties of that region are unknown. It might be denser or less dense than the G-cloud. It might have different temperature, composition, and structure. The journey through the galaxy is a journey through variable environments. Each region has unique characteristics. This cyclical passage through different interstellar clouds has likely been occurring throughout the solar system's history. 4.5 billion years ago, during the solar system's formation, it may have been in a different type of interstellar environment. That environment shaped the formation of the planets and the composition of the nascent solar system. Different initial conditions might have led to a completely different planetary system. Similarly, 50,000 years in the future, When the solar system is immersed in the G-cloud, the environment will be different again. Conditions on Earth will be different. Life on Earth will have adapted to the changed cosmic environment. Evolution will have continued. Civilizations will have risen and fallen. And through it all, the solar system will continue its journey through the galaxy, passing through clouds, encountering stars, and gradually aging. The thought of 50,000 years in the future raises interesting questions. What will Earth be like then? Will human civilization still exist? Will Earth's biosphere remain unchanged, or will it have evolved dramatically? Will technology have advanced to the point where humanity can deliberately protect against increased cosmic radiation? Or will humanity have spread beyond Earth to other planets, having already adapted to cosmic hazards through space habitation? These are questions we cannot answer. The future is inherently uncertain. But we can be certain that the solar system will continue its journey. We can be certain that conditions will change. We can be certain that in 50,000 years, Earth will be a very different world, orbiting the Sun in a very different galactic environment. 35. What happens? If you traveled beyond the edge of the solar system, imagine stepping into a spacecraft with unlimited power, advanced life support, and the ability to travel at high speeds. You're departing from Earth, leaving the solar system, heading into true interstellar space. What would you experience? What would you discover? The journey would be unlike anything humanity has ever attempted, a voyage through the most extreme and alien environments imaginable. The first leg of your journey would be familiar. You'd pass through the inner solar system, flying by Mercury, Venus, Earth, and Mars. You'd see the Sun as it truly is, a massive ball of plasma, far larger than anything on the planets. As you accelerated outward, the Sun would gradually appear smaller. The light and heat it provides would diminish. By the time you reached Jupiter's orbit, the solar radiation would be only 1% as intense as at Earth's distance. Continuing outward, you'd enter the realm of the ice giants. Saturn with its spectacular rings would appear as you passed. Uranus and Neptune would come into view. The darkness would deepen. The temperature would drop toward 200 degrees Celsius. The Sun would appear as a bright star, similar in intensity to how Venus appears from Earth. Beyond Neptune, you'd enter the Kuiper Belt. Here, dwarf planets and icy worlds populate the region. You'd encounter Pluto, a small world with mountains of water ice as hard as rock. Eris, slightly more massive than Pluto, would appear as you traveled farther. Each world would be a frozen relic, unchanged for billions of years. As you traveled through the Kuiper Belt, the density of objects would slowly decrease. Years might pass between encounters with significant worlds. The Sun would become just another point of light, indistinguishable from brighter stars in the sky. The radiation from the Sun would be negligible. You'd be entirely dependent on your internal power source. Entering the scattered disk, the objects would become even more sparse. Years would pass with nothing but empty space. But occasionally, you'd encounter a dwarf planet or large comet nucleus. Each one would be a unique world, with its own story, its own composition, its own history. The long journey through the near-empty space before the Oort cloud would be monotonous. Decades might pass with no encounters. The psychological toll would be significant. The isolation, the darkness, the knowledge that you are farther from humanity than anyone has ever been. The Sun would be barely distinguishable from other stars. Finally, you'd begin encountering Oort cloud objects. First, you'd see a few. Then, as you traveled deeper into the cloud, the density would increase. Small comets, kilometers in diameter, would appear regularly. Each one would be a window into the ancient solar system, preserving materials from the solar nebula 4.6 billion years ago. The journey through the Oort cloud would take years. The objects would gradually become fewer again as you approach the outer edge. The temperature would be near absolute zero. The radiation from cosmic sources would be intense. You'd be in an environment fundamentally hostile to life as we know it. Crossing the heliopause would be a milestone moment. You'd detect a sudden change. The magnetic field direction would shift. The particle density would change. Instruments would confirm that you'd crossed from the solar system into the interstellar medium. You'd have achieved what no human has achieved, a direct journey beyond the solar system. In the helios sheath, between the heliopause and the termination shock, you'd experience extreme conditions. Temperatures millions of degrees despite the vacuum. Intense radiation, complex magnetic field structures. It would be an environment completely alien to human experience. Crossing the termination shock would bring another dramatic change. The temperature would spike even higher initially, then gradually decline as you traveled farther from the shock wave. You'd be entering the truly open interstellar medium. As you traveled away from the solar system, the sun would gradually fade from view. After thousands of years of travel at relativistic speeds, the sun would become indistinguishable from other stars. You'd be lost in the galactic neighborhood, surrounded by stars, with no clear reference to where you came from. The psychological impact would be profound. You'd be completely isolated from humanity, separated by distances that light itself takes years to traverse. The interstellar medium around you would be your new reality. Tenuous clouds of neutral hydrogen, thin dust layers, the faint magnetic field threading through space, cosmic rays from distant sources, radiation from nearby stars. It would be an environment of profound emptiness, yet not truly empty. Matter exists, but spread so thinly that human intuition fails to grasp it. Eventually, you'd approach another star system. Proxima Centauri, the nearest star, would gradually brighten as you approached. After tens of thousands of years of travel, you'd finally reach a new destination. A new system with its own planets, its own mysteries, its own stories. What you would discover depends on Proxima's system. Does Proxima b have life? Does the system have moons or rings or asteroids? Are there other planets undiscovered? What mysteries await in that distant system? Only by making the journey would you find out. This thought experiment reveals the true scale of the cosmos. The distance to another star is so vast that traveling there would consume a lifetime or longer. The isolation would be absolute. Yet the universe is full of such destinations, each with the potential for discovery and wonder. For now, the Voyagers are humanity's emissaries to interstellar space. They carry our message outward. They gather data about the frontier. They represent our reaching beyond the world we know. In the distant future, when technology has advanced beyond our current imagination, perhaps humanity will make the journey that the Voyagers have begun. Perhaps we will truly explore the interstellar void. But until then, we can only wonder about what lies beyond the edge of our solar system.